Good morning. Good evening, ma'am.
Yes, sir. Good evening.
Am I audible?
Yes, sir. You are very much audible.
No need for any mic and all, no?
Yes,
Or
sir.
headset?
No, not required.
Okay.
Headset also not required. No, you are very
Okay.
much audible.
Thank you. Okay. Thank you. So I will share from here, no?
Yes, sir.
PPT.
Now, once the session starts, we'll remove this poster.
Okay.
Then
No.
you can share your the
Yeah.
screen will
Okay.
be free for you to share.
Okay. 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 Thank you.
Okay. Hello, sir. Ajay, sir, are you there?
Yes. Yes. Yes.
Okay. No, what we experienced for the past, 4 days,
Yes. Ah.
since they are now, the participants are faculty members, by 6
Ah.
o'clock only they'll be reaching their home.
Okay.
So initially go with a little low pace, then
See.
you can
Okay.
by 6:30 you can most of the participants would join. Then we
Okay.
can increase yours.
Okay, ma'am. No, ma'am. Basically, I am planning to explain two case studies. So that I will start by 6:30. Till 6:30, I will
Yes, yes.
go basics like IoT and ML. I think most of them will be knowing it. So
Yes.
that I will cover in slow pace till 6:30. So
Okay.
once a majority join, I will start with my case studies. Okay.
Yes, correct, sir. Yes, sir.
Okay. Okay. Already have they covered ML part, ma'am,
No, sir.
during
This
these
is the
days?
first time it is being introduced.
Okay. Okay. Okay.
Now, in the edge computing and fog computing, they just mentioned ML
Uh-huh.
and
ML.
agentic AI.
Yeah. Yeah.
Only
Okay.
how they can integrate with ML and other applications.
Uh-huh.
But now, what is ML? It is not being introduced so far.
Okay. I have only few slides regarding basics of ML, but still I will explain with that. No issue.
Yes, sir. That is
So
enough.
yeah, because you see, for last few years we are hearing this term, so I think most of them will be comfortable with ML. So
Yes,
what
sir.
they need
Yes.
is what can be done with ML. What
Yes.
next? So
That
I
is true.
thought I
That
will
is.
plan in such a way that what next can be done in ML. So anyway, I
Yeah.
will cover both. Okay, no issue.
Yes, sir. Yes, sir. Okay.
Good evening, everyone. We have only a few more participants. They will be joining in soon. We'll start shortly. Ma'am, shall we start or do we wait for some more time?
We can start. I think we can start.
Good evening, everyone. We now begin the first technical session of day 5 of the 6-day ATAL-sponsored online faculty development program on advancements in cloud and edge computing, research and industry perspectives, organized by the Department of Computer Science and Engineering, Adi Shankara Institute of Engineering and Technology. The first session of the day focuses on a highly relevant and interdisciplinary topic, which is IoT and machine learning, which explores the convergence of intelligent data analytics with connected devices to enable smart systems and real-time decision making. It is my privilege to introduce our first resource person for the day, Dr. Ajay Kumar, Professor and Head of the Department of Electronics and Communication Engineering at Adi Shankara Institute of Engineering and Technology, Kaladi, Kerala. Sir brings with him rich academic experience and strong expertise in emerging technologies. His insights into IoT and machine learning will provide valuable perspectives for both research and practical implementations. Sir, we are honored to have you with us today. I kindly invite you to take over the session and share your expertise on IoT and machine learning. Thank you. Over to you, sir.
Okay. I'd like
Yes,
to
ma'am.
add one more point. Dr. Ajay Kumar is also heading AI and IoT Research Lab at Adi Shankara, which is about 3 crore funded by MIT. Just for information to all participants gathered here.
Thank you, ma'am. Thank you for your introduction. So I will share my PPT.
Okay.
Okay, is it visible?
Yes, sir. The PPT is visible.
Is it moving now?
Yes, sir.
Okay, so yeah, good evening all. So thank you for this brief introduction. So before I start this session, I would like to thank Dr. Ramani Bai, who gave this opportunity to interact with you all. So as this topic of our FDP is advancements in cloud and edge computing, research and industry perspectives. So I would like to have an interaction with this particular topic called as smart environmental monitoring frameworks using IoT and machine learning practical implementations. So this is the topic which I will be covering today. So myself, Dr. Ajay, as introduced, professor in Electronics and Communication Engineering Department. So this will be the outline of today's session. So as I said, when ma'am invited me for this particular FDP, she told the topic will be IoT and ML. And I thought we are hearing this term for last few years, this IoT and ML. I thought all will be having that basic understanding of what is IoT and ML. And I thought how I should go ahead with particular this about this session. I thought I will share my research experience. So my research experience is through my lab. So I will explain in detail. So basically I will covering IoT, machine learning, and I will explain 2 case studies. First case study will be air quality monitoring system. So in that I will cover both IoT and ML aspects. And the second is regarding a flood prediction system, which is done by AWS and also river level forecasting and prediction. And here also I will share the IoT works and also ML works. So in between, if you have any query or doubt, you please interrupt me, no issue in that. So I am open to solve or open to share whatever I know. So as I said, I have a lab called a Center for AI IoT Innovation, which is in our institute. So it is fully funded by Ministry of Electronics and Information Technology, Government of India, for a project. So this project is undergoing now. So it's 2.5 years old. So still 6 months to be completed. So the main vision is to develop intelligent IoT solutions to solve environmental issues. So we have basically 4 to 5 objectives. So in that 2 objectives I will be covering today. So these are the objectives, as I told. One is to have a system which monitors the air quality. The other is to predict the flood, which is quite alarming thing in our area, which is Kaladi. And then another is to distribute water, smart water level distribution, and also to develop an startup ecosystem in our campus. So these are the different objectives in the project, which is funded by Ministry of Electronics and Information Technology. So I'll start with the basics of IoT, as I said. So I think all of you might be knowing what is IoT. IoT is nothing but Internet of Things. Here nowadays we call it as Internet of Everything or anything. So the things here, it may be any physical device, any living or non-living. So any things we can actually interconnect by using internet and sensors. So the basic element which is needed for an IoT network is actually sensor. So nowadays we have almost all sensors in all the fields. So actually research in sensor development is actually a hugely or a highly researched area. And nowadays we are concentrating on indigenously developing the sensors without depending on the other countries. So that is actually a hot topic, sensor development. So sensor is basically the element which is needed to actually develop an IoT network. And based on the application, we can choose our sensors. And another important thing which is needed in an IoT network is connectivity. So we need a stable and fast internet connection, so that the sensed data is actually transmitted or communicated with the end nodes. So what we call it as in IoT, as I told, we will be having physical things or living or non-living things. So we will be trying to connect those things by using a sensor. So what we call it as a smart object. So a smart object is the IoT device which we are actually concentrating here. So that particular smart object will be having sensor. It will be having a processing unit. It will be having a memory, and also it will be having a communication device. So basic idea here is to collect the data intended based on the application by using sensor. If needed, it can be processed in that particular smart object itself. And actuation. Actuation is the action which has to be done based on the data collected. So that can be done then and there itself, or otherwise you can use that data, you can analyze that data, you can process that data, you can store that data. All these things are possible either in the edge or in the cloud. So those things are based on the applications. So basically what we call it as a smart object. So smart object is actually a basic ingredient in any IoT network. So as I told, we'll be having smart objects, and next is to have a gateway. So a gateway is for the, so to route this data. To route this data, if you are using a cloud, we have to send this data to cloud for further processing, analyzing, and for further enhancement of the data. And at the end, if you are going to display it, you can use a display. Or if you are pushing that to a website, you can do that. Or if you are pushing that to a mobile app, that also can be done. So all these things are done in next stage. So once all these things are done, so the basic thing is you can integrate cloud. So integrating cloud means you have to apply some of these algorithms for analyzing the data. So based on the application, you can go for any type of analytics which is needed. So that is the beauty of IoT. IoT is actually an enabling technology for AI, an enabling technology for blockchain, an enabling technology for terahertz communication, for 6G, 5G. So it's actually a technology which can be synced with any of the developed or newly developed technologies. So that's why we concentrate nowadays. We are concentrating on integrating AI with IoT. So IoT generally means Internet of Things. So if you are actually using AI with IoT, we call it as IIoT, Intelligent Internet of Things application, or IIoT applications. So this is intelligent Internet of Things, that is intelligent IoT. So intelligent IoT, so roughly or barely you are actually receiving the data or raw data, and you are doing nothing, or you just displaying that particular data means there is no use. So that's why if you having a data, you need to use that data for a meaningful application. So for that, this AI will help us. So AI-driven adaptive and predictive IoT systems are quite common nowadays. So how it will be intelligent? So integration of IoT with intelligent decision-making capabilities based on AI, ML and data analytics. So these are actually the enabling technologies which will help IoT to make the solutions intelligent. So that is one of the goal of our lab, to use this machine learning, this deep learning and also AI algorithms to make it so to generate intelligent IoT solutions. So that is our goal actually. And IoT data is actually enriched with the AI and data science techniques to enhance this decision making, automation, forecasting, prediction. All these things can be done by using this AI. So normally, if you think about a factory, so normally factories will be having machineries, equipments, etc. So to maintain those machineries or factories periodically with manpower is actually a huge task. So if you have some kind of an IoT network with ML inbuilt on it, so it will actually parallelly it will check the condition, how the health condition of all these equipments, all these this machinery, so that if any anomaly is detected, it will immediately inform and it will take measure. And like based on the application, you can go and explain how an ordinary IoT application can be done, or it can be extended or enhanced to intelligent IoT applications. So this is the topic, intelligent IoT applications. Next, I would like to discuss about few IoT levels and deployment templates. So as I told, IoT can be deployed in any levels. So based on the application, as I told, we can have different types of deployments. So first we'll see level 1 kind of deployment. So this is our IoT level 1 deployment. If you see here, we have only one node. One node means, as I told, a node will be a smart object. And that node, it is connected with the resource, and we have a controller service here. So it has a single node that performs sensing or actuation, stores data, performs analysis, and hosts the application in the local itself. So even though we have cloud, in IoT level 1, we are using only the local. We are hosting that particular deployment in the local itself. So these systems are suitable for modeling low cost and low complexity solutions where the data involved is not big and the analysis requirements are not computationally intensive. To explain with an example, say simple smart lock. So a lock that you can lock or unlock by using an app which is there in your mobile. So with basic status reporting, all within that particular own system. So we are not actually using any cloud or any other memory. We are using a mobile app which is there in deployed in local, and you by using or operating that particular mobile app, you are actually opening the lock and closing the lock. So that is one smart application which can be done. This is actually the basic implementation of IoT. So simplest way of implementing an IoT network. And there are so many other examples also. For example, temperature monitoring and displaying it in the in a display. So it will be having a sensor to actually monitor the temperature, and automatically it will display the temperature value. So that is actually a simple kind of implementation without much complex integration of cloud or anything. So this is actually IoT level 1. So next, IoT level 2, if you see here also we are using only single node. The thing is, we have integrated cloud here. So it will be bit complex than level 1, but not that much complex, because here also we are dealing with light data. So data is stored in the cloud, and the application is usually cloud based. So you're actually using cloud for storing the data. Clear? Only for storing the data. So it is used where the solutions involve a big. However, the primary analysis requirement is not that much computationally intensive, and analysis will be done locally, but only the storing purpose will be using the cloud. For example, in smart irrigation system, where the moisture level of the soil will be sensed by a sensor, that will be an unit. So once that level is below a critical level, automatically what we need is we need to water it. So that can be done then and there itself. So automatically it will open the valve and water will be sprayed. So if you need, that data will be stored in the cloud. So that is for future, actually for future use. So, but the action will be done locally. So no need to wait till the cloud sends a message that you have to water. So actually the watering will be done then and there itself when it detects that the moisture level is very less. So that is one smart application which can be deployed by using this level 2 kind of an deployment. So I hope this is also clear. So here also, if you see, we are using only single node. And third level, that is IoT level 3. Here, the cloud is used for not only for storing, but also for analysis also. So the analysis requirements are also done in cloud. So this is little bit computationally intensive than the previous one. So to explain with an example, a smart city traffic management, where sensors and cameras actually deployed, they feed traffic data to the cloud. So it will be in cloud that will be analyzed whether they are misusing very untoward incident happens or any traffic violation happens. It will be analyzed in the cloud and automatically the measures will be taken. And also it can be used to reduce congestion. All these things can be done in the cloud. It is not locally done, but it will be analyzed in the cloud and the instructions will be coming from the cloud to the central manager. Okay, if you see here, we have a controller service, so which is connected to the cloud. So the instructions will be coming from the cloud to actually actuate or to do action, some kind of action. When compared to level 2, level 3 differs in that in level 2, actuation will be done locally, whereas in level 3, to do action, the instruction should come from cloud. So that is the difference between level 2 and level 3. And next, if we go for level 4, this is a bit more complex. As we move along, the complexity becomes like increasing. Complexity increases. So here we are dealing with more than one node. So it is not a single node system. Here we are actually having multiple nodes, and we have two important things here. One is the observer node. So if you see here, one observer node is there. So the main purpose of this observer node is to get data from the cloud. Okay, it will coordinate data with the cloud and it will be actually analyzed and it will be used in the local. Okay, so here also we have an observer. So this observer node actually is connected to cloud. So the main purpose is the observer node, which can subscribe to and receive information which is collected in the cloud from these particular IoT devices. So where these actually IoT level 4 is used where multiple nodes are required. So till now we have seen systems with only single node, but from now onwards we'll be seeing the applications wherein we need multiple nodes, and data involved here will be very big, and the analysis requirements are also computationally intensive. So for example, we have industrial asset monitoring system. So as I told, in industry we'll be having different machineries. So vibration, temperature, pressure, all these sensors will be actually deployed or connected with all this machinery, and local analysis to detect anomalies will be done. That, as I told, in level 2. This is a bit more complex. So here it will send critical alerts and those summarized data to the cloud. So here predictive maintenance is also possible. So in previous case, when I explained this particular example, predictive maintenance was not there. So if you need a predictive maintenance, so it will predict that this machinery has to be maintained, or some maintenance has to happen in a particular machine or particular equipment. So that is only possible if you have a cloud and also the data is analyzed in the cloud and some kind of AI algorithm is run in the cloud so that it will predict that maintenance is needed. So IoT level 4 is also most commonly used deployment template. So this is one application we have. If you think, you can have multiple kinds of applications by using IoT level 4. And also in IoT level 5, here also there are multiple nodes. And one important thing is here we have another node called as coordinator node. So since we have multiple nodes, so this coordinator node collects data from the end nodes and sends to the cloud. Okay, we have a common coordinator here. So that coordinator node will collect the data from all these nodes. Since we have multiple nodes, we need to have some coordinator to collect those data, and he will collect all those data and it will be sent to cloud. So that will be the only difference between level 4 and level 5, the introduction of coordinator node to much more streamline the application. So here, if you go for any examples of environmental monitoring, which we have implemented, I will explain it with a case study. So we have multiple stations deployed for monitoring the environmental parameters. And we will be having in central, we will be having a node who will be collecting all this data, and it will actually send to cloud. So level 5 is also most commonly used deployment. And the last deployment is what is called as IoT level 6. So here, if you see the difference, only the difference is we have a centralized controller. So here the centralized controller is aware of the status of all end nodes and sends control commands to the nodes. So here in between this coordinator node and the cloud, we will be having a centralized controller. So here the centralized controller will do the role of coordinator node as well as the role of observer node also. So observer node also will be aligned in with centralized node. So the centralized controller, he will control cloud as well as the end node. So you will be actually acting as a bridge. So this is also most commonly used template, wherein we are thinking about a large deployment of IoT network, like a smart city infrastructure, where multiple kinds of architecture will be there. So for example, for street light, we will be having a one architecture. For water distribution, another architecture. Okay, so likewise for traffic management, we will be having another architecture. So like if you have multiple architectures involved in a single network, we should go for such network wherein need a centralized controller. So this IoT level 6 is the most complex system or architecture where it will be used only in such cases wherein if you are in different heterogeneous kinds of deployments. Okay, heterogeneous kinds of deployments in a single IoT network. In those cases, you have to go for IoT level 6. So once again, I will brief all these levels: IoT level 1, 2, 3, 4, 5, 6. So level 1 is the simplest level, wherein we have only one node and we will be doing the processing in the local itself. In level 2, we will be using cloud for storage. Mostly the action will be done in the local itself. In level 3, both storage and actions are performed only after getting the instructions from cloud. And level 4, here we have multiple nodes and we will be using cloud for analysis and for also storage and to give instructions to the nodes. And in level 5, it is a bit more complex than level 4. Here we'll be having a coordinator node. Since we have multiple nodes, the coordinator node will coordinate and it will send data to the cloud. And level 6 is the last level, wherein if heterogeneous networks are in a single IoT network, we have to go for IoT level 6. So this is regarding different deployment levels of IoT. So if you see the research perspective, so recent research highlights the need for integrating data science and IoT to achieve intelligent decision support. So addressing challenges such as security, privacy, and adaptability in IoT ecosystem. So we have to integrate all these data, which are collected by using sensors. So we need to analyze all these data, otherwise it will be a waste. So once we can find some kind of pattern or some kind of meaningful way of things from this data, you can use and you can act on this data. So for getting data, you need to deploy IoT. So that's why IoT is used for getting the data, and AI is used for analyzing an action, for performing the action. So that's why the convergence comes AI IoT. So AI IoT is predicted to transform numerous domains, including healthcare, smart cities, industrial automation. So many fields you can integrate AI and IoT, and you can bring remarkable changes. Okay, so simply using IoT, you can perform an action, but if you are integrating AI, so it can do wonderful things. So some of the examples I will explain in coming slides. So ultimately, my aim is to cover both this, how AI and IoT is integrated. So again, I will brief machine learning also. So I hope all of you may be knowing machine learning. So machine learning is a subset of AI that enables systems to learn patterns from data and make predictions or decisions without explicit programming. So some kind of patterns will be recognized or classified based on the data that we are actually imparting to the machine. So that machine learning is actually a subset of AI. So, and also in IoT, ML transforms raw sensor data into actionable insights. So as I already discussed, if you are integrating IoT with ML means, as I told, IoT can generate data and ML can actually transform those data into some actionable insights. So some of the applications, air quality prediction, flood level water forecasting, these two things I will be explaining: weather prediction, disease diagnosis, image and speech recognition, smart traffic control, customer segmentation. So all these things can be implemented. So we can implement both this IoT and ML or AI IoT in all these field. Again, if you classify ML, these are the broad classification: supervised learning, unsupervised learning, reinforcement learning. In between, we have some unsupervised or semi-supervised learning. So all these things are the different classificational techniques of ML. So in supervised learning, you will be using labeled data. So if, for example, for air quality prediction, you will be using some kind of gases or the parameters which are actually degrade the air quality. So they are actually labeled. So that's why they are called supervised learning. So in unsupervised learning, so we are not dealing with unlabeled data. We are not dealing with the labeled data, but the data will be different. So we need to have some kind of clustering or some kind of mechanism to find out the behavior. So that we call as unsupervised learning. So in reinforcement learning, actually the machine will learn with the trial and error method. So for example, driverless car, all these are examples for reinforcement learning, and all these fields, so like as agentic AI and all are coming. So they are all actually booming the need for reinforcement learning in machine learning applications. So this is the broad classification of ML. And this will be the workflow of ML. So as I told, data collection will be the first thing. So that can be in real time, that can be by using IoT nodes. If you are going for a real-time application with ML, so data can be collected with sensors, and it will be from an IoT node, and that will be passed to next stage. The first stage of this ML will be the pre-processing. So in pre-processing, actually, we'll be doing the cleaning. So actually, the data which is received from an IoT node will be inconsistent, or we have to fix error, or sometimes there will be missing of data. So all these things can we have to do, or we have to perform all these things before we feed that to our ML algorithm. So that is our first stage of cleaning. And then normalization is another method. Actually, if you see, it is another important pre-processing stage wherein we are actually either we are scaling it up or scaling it down. So that process we call as normalization in order to generalize the data, so that some dominating features will not be highlighted, or some dominating features which are there in the data will not shoot up. Okay, so that's why we are normalizing the data. And also we have feature extraction, that is barely, so the bare or raw data will be converted to some meaningful data. So these are some of the procedures which are used in data pre-processing. And then once this is done, our data is neat and clean. So we can use those data to train our model. So again, that model, we as last slide we have seen, we have different types of model. We can choose any of those model, and we can come with some kind of learning patterns by using the data. So that we have to find which model works fine. That will be actually a trial and error or experimentation process. We have to run all these models. If we need, based on the application, we have to come up with a suitable model for the application. And the next stage is to use the AI algorithms for prediction and analysis, or we can forecast or predict or detect. So all these things can be done by using this model. So again, the accuracy depends upon the model. So this can be done in the next stage. And last stage, we can give alerts or insights, or it will be the output. So what we are going to do with that particular model, or what that machine will actually do. So that will be the output. Input will be the data, output will be an action. Okay, so action in the sense it can be a message, or it can be a signal, or it can be an information passing to users based on the application. So that will be coming out of that particular model. So this is a general workflow. So again, this workflow I will explain with an example. So with the case study. So how this slide is to show how that particular ML or workflow will be followed in any machine learning technique. So again, the IoT and ML. So IoT focus on connecting physical objects to the digital world. So by real-time sensing of physical and environmental parameters, large-scale deployments of interconnected device, reliable data acquisition and communication. So all these things IoT will focus. On the other hand, the machine learning will do its part by learning some patterns or trends by using this data set, making some predictions and informed decisions. And also, this is actually a continuous process, whereas continuously it will improve the performance. How long the data is like extended, that long the performance also will be improved. Like bigger the data, more the performance. So we are asking the machine to learn. So we need to give the data. So the data, we have to give a trusted data. We have to give a neat and clean data. Once we give that, the machine will learn and it will predict or it will forecast. So to summarize, IoT will provide data and ML will provide intelligence for applications. So that's how this IoT and ML are blended or linked or synced or whatever you can call it as. So that's why IoT and ML are actually plays very important role in modern day applications. So these are the case studies. So yeah, 640. Okay, these are the case studies. So I'll be explaining. So first is the air quality monitoring system and second is the flood prediction system. So these are the some of our products developed in our lab. So this is actually the air quality monitoring. So AWS station, which is developed by our lab, and this is level sensor developed by our lab. This is AWS again, and this is actually the AQMS, air quality monitoring system, and this is actually the indoor air quality monitoring system which is developed. And all these products are developed by our faculty or staffs in our lab. So we'll start with the first case study. First case study is air quality monitoring system. So as I told, we have used IoT and also we have used AI. So first we'll see the IoT part, that is the hardware part. So in the hardware part, we have sensors. We have AQI sensor, we have temperature, pressure, humidity, and we have different gas sensors like NO2, NH3, SO2, CO. So likewise, we have so many gas sensors. Again, all the data will be collected by using these sensors. And we have used ESP as our microcontroller. And also in some of the application, we have used GSM also. And also we have used LoRa. So based on the terrain and based on the place where this particular device is actually deployed, we have used the communication technology, either LoRa, GSM or Wi-Fi. So as I told, sensor will generate data and we have used a microcontroller and we are using the connecting technology and it is connected to the cloud. So this is the hardware part. And next is the AI part. So in AI part, as I told, we have used different sensors like PM 2.5, PM10, CEO, NO2, SO2, NH3, all these sensor values we are actually collecting. This collected data is pushed through LoRa to our web app, to our cloud. And in the cloud, we are performing the AI algorithms, or we are using AI algorithms or deep learning algorithms to forecast and also to predict the air quality in coming days. So, and that is visible in our application, web application, which we call as AirAware. So in AirAware app, if you go and see, there will be a real-time visualization of the AQI value in the deployed states. And also there will be forecasted levels and also location-aware air quality insights. So that is one of the novelty which we have brought in this particular project, and also health risk alerts. So all these things are some of the systems which we have developed, which is the novelty of this particular project. So this is how we bring in AI into this context. And if you see here, this is the actually this map shows the Karadi Panchayat here. So this is the area, and this is where we are, Adi Shankara Institute of Engineering Technology, and we have deployed one module here and one here. So totally we have deployed 5 IoT modules to predict air quality monitoring. So to predict air quality. So all these deployments are like, for example, deployment in Karadi Gram Panchayat here, we mostly concentrate on CO. So carbon monoxide, because it is hugely involved with the traffic data. And here, this is mostly depending on NH3 and SO2 because an industry is nearby here. So based on the area, what type of sensors you need, you have to use those sensors to predict the air quality. So air quality is predicted by using AQI, as we all know. In order to calculate AQI, you need at least 3 different parameters. So that three different parameter you can choose based on your location. For example, in our college, if you are going to predict AQI, traffic has no role to play because traffic is not that much a severe issue in our college. So we can go for other parameters. Okay, so whereas in Grama Panchayat, if you are going with the NH3, there will not be any use because there is no industry involved in this particular area. So the mostly in the area is covered with the traffic. So we have to go with carbon monoxide or carbon dioxide or even any other poisonous gases to calculate the AQI. So all these places we have calculated AQI, and one more technology we have developed, I will explain in the coming slides. So this is the equipment, air quality monitoring station or system which we have developed. So we have deployed particulate matter sensors like PM 2.5 or PM 10 and gas pollutants like CO, NO2, SO2, NH3 and O3 based on the area. Okay, based on the area, and also some meteorological parameters like temperature, humidity, pressure, which will be common in all the hardware modules. So again, if you see how to predict this AQI, we have used the technology. So again, how to predict, so how to forecast, how to use this AI in AQMS. So AQMS, as I told, air quality monitoring station. So this environmental data actually exhibits temporal dependency. So temporal dependency is basically depending on past data or to analyzing the past data. So last year or last month, how was the air quality in this particular area? Those data we call as temporal data. And also there are some seasonal patterns, like if it is a festive season like Deepavali and all, obviously the atmosphere will be surrounded with crackers and all, so that will actually ruin the atmosphere, the air quality. So that is also considered, and also non-linear behavior. So if something happens in an emergency case, so that also considered. So by considering all these 3 parameters, like past data, what happens in seasonal, and also some non-linear behavior, in the sense some kind of urgency situation, some kind of disaster happens suddenly without any prior indication. Like for example, say fire accident happens, so that automatically emits poisonous gases. So those kind of situations also we have used for our model. We have trained with those data also. So again, in machine learning, by using machine learning, we can find out a pattern. We can actually forecast the air quality, and also we can make decision proactively without waiting to get instruction. It will act then and there itself. So that ML actually provides the insights to act. So that is the air quality is alarming, so we have to do something. And also, as I told, personalized health risk is also involved here. So a person who knows his health condition, and this AI model will tell him that since your health condition is very bad, in coming days, the air quality will be very poor. So you have to take precautions. So all this decision-making process will happen in this particular model. So, so we have implemented, if you go with the ML, we have implemented 4 types of ML DL algorithms like LSTM, BiLSTM, GRU, and BiGRU. So these are the pollutants which we have used: PM 2.5, PM 10, SO2, NO2, CO, NH3, and O3. So we have calculated AQI, air quality index, by using Central Pollution Control Board formula. So the Central Pollution Control Board actually has a formula in order to predict an AQI. At least you need to use at least any of these 3 parameters, either PM 2.5, NO2, CO, or NO2, CO, NH3, or like any of 3 parameters can be used to calculate the AQI. So there is a complex formula for that. So for that, we need at least 3 input from these particular things. Apart from these things, any other that can also be added, but 3 different parameters are needed. So we have actually checked with our Kerala State Pollution Control Board also. So our module, which we have developed, we have kept it in the same area where the KSPCB board is also deployed. and we have cross-checked the values. So what our module is actually displaying, and also what the Kerala State Pollution Control Board is displaying. So almost the values are similar. And also, as I told, in coming to the models which we have developed, we have implemented all these 4 models, and these are the evaluation parameters for our trained data. So if you see MAE, MSC, that is mean absolute error, and MSC, RMSC. So LSTM model, GRU model, and also by GRU model and by LSTM model. So we have selected GRU. So it is not that GRU will be the best model for every application or all the application. So in this particular case, in this particular application or in this particular experimentation, we feel that GRU is actually computationally lower computational complexity, and the accuracy of prediction is more, and the training is faster, and deployment and maintenance is easier. So we have come up with GRU. So GRU is the model or deep learning model which we have used in our application. So these are the comparison with the other models. So we have chosen GRU as our perfect model. And these are some of the results of GRU, LSTM, and the other 2 algorithms for a single case like SO2, for forecasting SO2. So SO2, so that blue line indicates actually the forecasted model. That red line indicates that original value which has happened. Okay, so this is the results. And as I told, one of the novelty in this particular project is spatial interpolation. So in spatial interpolation, I will explain again with that map. So here, if you see, if you take this particular area, we have stations deployed in 5 different locations, 1, 2, 3, 4, and 5. So normally what happens is, so if you are here, if you are, suppose imagine you are here in this particular place, if you check the air quality of this particular area, normally what happens is the nearest or the station which is near to this place, which will be the Adi Shankara Institute. So this value will be shown. Like you are here and nearby you have an industry here, but still if you check an air quality here, the air quality will be very good because that will be the air quality data from this particular institute or deployed with this particular module or whatever the hardware which is deployed here. Okay, so again for here also, so this is a common issue or common problem which is there in our country. So and again practically placing these hardwares in all the location is impossible. So again, the cost wise, complex wise, algorithmic wise, it is very huge task. Like we cannot like implement or we cannot deploy these hardware modules in each and every place where you go. So the only solution here is to go for a technique called as spatial interpolation technique. So this is the technique which makes, or we have different types of spatial interpolation technique like Kriging model, empirical Bayesian Kriging, inverse distance weighing. So we have so many types of like interpolating techniques. So what done in this particular by using this particular technique is we are actually interpolating the air quality data from that particular space where that person is standing with either by using all these deployed sensors or by using different sources which is surrounded. So all these things are done mathematically, and we have the results which will be like which will tell that particular person the actual or almost similar or a true kind of air quality at that particular place. So again, that is actually measured, and also it is coming up that the Kriging model that we have developed, we have used all these models, and Kriging model is showing the best result. So like how we tested means actually we took a mobile air quality monitoring station and we took data from that particular unlocated station, and we actually interpolated by using this technique also. So when you compare, the Kriging model is actually showing the comparable results with the actual that station value. So this is one technique this is one of the novelty in this particular project, that is spatial interpolation. So this is I'm ending the case study 1. So this is in case study 1. I will brief here. So what we have done is we have deployed 5 different hardwares. So each and every hardware is actually an IoT hardware which has different sensors deployed, and the type of sensors depends on the area. Okay, and also what it is surrounded. So different sensors deployed in an IoT hardware, and we have deployed it in 5 different locations, and we have used deep learning algorithms for the forecasting and also for prediction of air quality. So forecasting is based on the past data, and prediction involves the current data also. Okay, so that is the difference or similarity what we are calling forecasting and prediction. So that is done here. So this is our case study 1, and in case study 2, so that is case study 2 is actually space flood water or flood prediction. Okay, so again, if you some of you might be knowing, our college is in a place called as Kaladi, and near to Kaladi we have a river flowing called as Periyar River. So this Periyar River usually floods. So especially during monsoon season. So due to the rise in water level, the surrounded area of this particular river is actually flooded. So we thought of coming up with an intelligent IoT solution to give an early alert to the people who are located nearby those location, so that they can shift or relocate from that particular place. So the problem with this thing is, if you simply tell that the flood will happen tomorrow, or flood will happen day after tomorrow, or the water level will rise, people will not move, or they are not willing to move from their home place. So we have to give them a trusted information. So trusted information, for getting the trusted information, we have incorporated explainable AI here. So in this particular application, we have used explainable AI to impart the trusted information which is needed to be like displayed, or to be like given to those people who are living in that particular place, so that they will be convinced and they are ready to move from that particular place. So the input, if you see, we have taken different types of input in order to get that particular project done. We have used wind direction, wind speed, temperature, pressure, humidity, water level, and again dam water level, and also rainfall intensity. So there are so many parameters which are influencing the water level. So again, we have a dam, nearby dam we call as Bodhatangattu Dam is there, which is around 40 kilometers from the Kaladi. So again, the catchment area of that particular dam is again around 25 square kilometer. So the thing is, we have deployed our automatic weather station, so which is the weather station, and we have deployed in the catchment area of that particular dam, and we are getting the rainfall data. So that is actually a major contributor to this particular water level. So again, by using AWS automatic weather stations, we will be getting the rainfall intensity, and also we have placed a level sensor in the Kaladi River to get the level of water. So water level, to know the water level, and we have used LoRa gateway or LoRa connectivity to integrate all this data and to send to cloud. In cloud, we'll be performing our deep learning algorithm, and the flood will be forecasted, and that is available in the web page and also in the app, the same app which that is AirAware app. So this is the basic idea, and this is the hardware. In hardware, as I told, in sensor, we go for rain gauge to predict the rainfall intensity, wind direction, wind speed, temperature, pressure, humidity. All these sensors are actually in that particular module. And we have used again a microcontroller, and we have used LoRa, and sometimes we have used GSM. As in interior places, LoRa is not practical, so we have gone for GSM, so or 3G SIMs, and then from there we have pushed the data to cloud. So this is the equipment which we have developed, AWS automatic weather station. So again, this is the unit which will measure the rainfall, and this is the unit which will measure the wind speed. So again, pressure, temperature, all these sensors are placed in this particular module. So all these things are developed in our lab, and these modules are also fabricated in our lab. So this uses actually tip-in bucket technique to calculate the rainfall intensity. So So this is the hardware which we have deployed. We call it as AWS V1 and V2. V1 is the version 1 and V2 is the version 2. And this is our application. So web application, which is Air Aware. As I told, this is the one app wherein you can see all these data displayed. So predicting the water level of Periyar River 6 hours ahead using ML is our challenge. So we are actually predicting the river water level 6 hours. So we are actually predicting the water level after 6 hours or hour by hour up to 6 hours. So that is actually an input and a reliable input for the people who are living nearby, because the major source of flood is the rise in river water level. So if you know what will be the level of the river after 6 hours, you can take precautions or you can take necessary actions. So the problem nowadays which the people are facing is they are not knowing whether the water level rises or whether the water level will be decreased or it will be like gone down, because they are not having any knowledge about what is happening in the catchment area or what is happening in the area wherein the source of this river, the water is coming, that is from the Budaktangattu Dam. So during a heavy monsoon, the whole shutters will be open. So that the discharge of water will be huge, and people, as we all know, we cannot predict the rain also, and sometimes alerts are given, but still we cannot know like what is happening in that particular catchment area. For in order to solve this problem, we have come up with intelligent solutions of installation of AWS, and we have collected all these parameters and we have gone with a model, an LSTM model. So as I told, data sources are dam operations, like dam discharge value, rainfall data, opening and closing of shutters. So all these are one of the inputs. And the river levels, river levels, we have Neelishwaram is one of the place before Kaladi. So before Kaladi, we have an Neelishwaram where Central Water Commission, they are displaying the data. So that data is also taken into account. And also we have placed our own device which will measure the river water level. So by taking all these inputs, we have fed that to an LSTM model, which will actually forecast the flood. So this is the thing. So data ingestion, we have already discussed. We have multiple kind of data like rainfall and water discharge data, level data, and also the data from the catchment area. So all these data we are actually passed through pre-processing stage, where we have used our normalization and also our cleaning process. And after that, we have gone through feature engineering or feature extraction phase. So after all this process, we have made the data ready. So in that data, we have used around 70% of data is used for training and 15% for validation and 15% for testing. So and we have introduced an optimization technique also. So sometimes overfitting of data will happen. So that we have to stop. Sometimes the machine will learn or saturated and it will learn. So that kind of overfitting also we have addressed. And this is the number of neurons 128, 64, 32. And we have used Adam optimizer with the learning rate of 0.001. And these are the values. Epochs is 100, and also around 50,000 data. The size of data size is 55,000 with a batch size of 32. So these are the some of the configuration of our LSTM based flood forecasting system. And these are the results. So if you see here the blue line and green line, so the green line is actually the forecasted value and the blue line is actually the actual water level. So there are some minute difference, but they are in millimeters, so it will not affect much. And these are the values which are displayed in our website, like 5.06, 5.43. All these are forecasted values. So some are in orange because it is crossing it is giving that orange alert because it is crossing the target level, and after this it will give the red alert. So at that point of time, people have to evacuate from that particular place because it is danger, it is going to flood. So because of this particular river. So this is taken in one of the days during the monsoon. So this is actually like if you see here, the current water level is 4.89. So next hour it is predicted as 5.06 meters. So So this is the prediction which we have introduced by using this particular algorithm model and through this project. So this is our actually result, one of our result. And as I told, we have used an explainable AI solution in this particular thing simply because in order to convince people that the information which is provided by this system is actually a trusted information. And so we have used an algorithm called as line. So this actually helps us in giving a distributed kind of value. We have also tried with shape, but Lime actually produces a little bit more reliable and actionable data. So we went with the Lime model. And these are the websites which we have referred. So as I told, we have almost we have taken all the data in this particular which are available in the websites. Even though they are available, sometimes those data are actually past data. So we have taken data from 2015 to 2025. So around 10 years data of rainfall and also regarding air quality also. So I will show you the website. So this is our website. So this is our air aware. So this is the one place where you can
Sir,
see
your screen is not visible. I think
not
you
visible.
have shared
Okay,
only this presentation.
okay, ma'am, I will
Yeah.
share that.
Okay.
One minute, ma'am. Is it visible, ma'am? Ma'am, is it visible now?
No, sir.
I'm in
No,
mode.
sir.
Actually, I was responding. Sir, you have to close the. Yes. Again, you have to share
Okay,
your
okay.
entire window.
Yeah. Is it okay now?
Is coming up.
Yes, sir.
Yes.
Yes, sir.
Okay. So this is the website which
Now
I
it's
was
visible.
referring. AirAware. So if you see here, so it is giving the values of air quality. This is one of our station, which is our campus station, which is showing it is as satisfactory. You can go for live AQI. So these values are given here, current readings. So again, forecasted values are also available here. So, and then coming to home, so we have water or weather station. Again, we have two stations here. So it is not visible here. We have two stations. Yeah. Yeah. These are the two stations, weather stations, which currently functional, and two stations we are planning in the catchment area of Budatangettu. One is in Kuttambuda and the other is in the Ayambuda. Okay, so yes, and then we have so many informations mentioned in our website also. We can go through that information. Okay, okay, this is what I intended to present. So if you have any query, I'm ready to answer. So once again, I will share the PPT. If you have any query, please you can ask here. And this is the team.
The participant.
You can email me also. So this is my details. So if you have any query, I'm ready to answer. I'm free to answer.
Dear participants, if you have any queries, you can ask them to sir right now. We have some time before the next session begins.
Sir, I need some details from you.
Yes, ma'am.
So the IoT product, basically, the performance and the efficiency of the IoT product basically depends on the quality of the sensors that we use.
That's correct, ma'am.
So can you share some indigenous affordable sensors where from we can get it?
One thing is all these sensors are imported from like foreign countries only. But there are some sensors which are indigenously developed by CMET and also from CDAC and all.
Okay.
But again, if you compare those values with those sensors which are available in the market, it will be different because each and every sensor is using different technology for getting the data. So some in the case of air quality monitoring, some sensors they are using some chemical reaction to find the value of the that particular pollutant. In something, it will be using some kind of photo resistance technology, and like by using light and all. In sometimes it may be using simple like for example, in case of PM sensors, it will be using the to measure the size of that particular sensor. So likewise, the technology is different for different sensors, and you cannot compare two sensors because two sensors may be using different technology to find the same pollutant value. And we have used many of the sensors which we have used are from CMET. So they have directly given us the sensors. And some of the sensors which we have procured from the market are from an agency called as Prana Air. So they are actually one of the company or one of those companies which are involved in air quality monitoring and deploying air quality monitoring stations. So since we are using those values for research purpose, they have like given us those sensors. And also there are so many sensors which are already available in the market. So you can buy those, but the difference between an industrial grade sensor and a normally sensor will be the duration and also how long it will survive, because we are deploying it in the outdoor conditions. So in outdoor condition, so it will all these environmental parameters will affect all these climatic changes like sunlight, even heavy rain. All these things will affect the value of the sensors. So the duration depends upon the quality of the sensor. Again, quality will depend upon the cost. So how much you are ready to like pay for getting those sensors. So to get really good sensor, it will be around lakh rupees. But again, in 500 rupees, you will be getting sensor. So the difference will be how long it will survive and then how accurately the data is like fetched. So again, to add to this particular thing, so we need to calibrate all these sensors. So it is not that once you deploy the sensor, lifelong you will get the data. So the thing is, you have to calibrate all these sensors regularly. So with for example, we used to calibrate every 2 weeks because since we are trusting on those sensors, we need to calibrate all those deployed sensors by using some kind of a calibration mechanism. And also we have another application of our machine learning, that ML, is to actually detect the anomaly. So sometimes all these sensors may be faulty and they will be giving us the wrong data. So we need to identify whether the data received is correct or not. So we have kept a target level, and that machine learning algorithm will check whether the received data is in between that level. If it is not, automatically a red signal will be given that some kind of anomaly is there in that particular area. So but that particular hardware. So again, we have kept a check in the sensor value also. So that is one thing. And again, you asked regarding the sensor. So we have gone for a CMET sensor and also Prana Air sensors.
Okay, sir. Sir, I heard now some exposure to IEEE sensors. Is there any such chapter? And
yeah, IEEE sensor chapters is there, but they are not involved in manufacturing sensors or not. But the only things they are, as I told, the research in sensor area is actually a huge area wherein people are involved in developing those materials which can be used to like fabricate a sensor. So most of the works are published in IEEE sensor journals. That is actually material science works And again, those works need like those kind of materials which are readily available. So in India, we are actually shortage of all these materials which are actually used for fabricating the sensors. So nowadays, graphene is used as one of the alternate solution for fabrication of sensors. And sometimes we were using silicon wafers as the ideal material. And like new materials are coming. So ultimately, all these works are published in IEEE Sensor Journal, and they don't have any like company or such kind of thing wherein they will provide sensors and all. Works are available in those journals.
Okay. So that because of the cost.
Yes, ma'am. Cost we can like if you are informing or if you are conveying that the values or the sensors are used for research, then they will definitely reduce the cost. As I told Prana here, so we inform them that all these sensors are used for deploying for a project which is funded by government. So they automatically like gave us the concession, and they trusted us, and we are in touch with them.
Okay. Okay.
So we are in touch with them. So actually, they are also monitoring our work because ultimately we should not harm their work because they are actually a solution provider in this area. So actually, we are in touch with them. They are also like in touch with us, like what we are doing. They are also closely monitoring. So it's actually basically sharing the data, sharing the information, sharing the knowledge, what we have, and getting the knowledge from their expertise also. So some people will help like giving subsidy or concession, but again for that kind of project, sometimes you have to go with readily available sensors which are readily available in the market. And so again, you have to experiment with different sensors. And we have to come up with some kind of experimentation data because otherwise you cannot say that deploying one sensor value and claiming it as the accurate value will not be a correct way of doing that. We have to try with different sensors and also pollution control board. They have certain kind of sensors deployed. That is actually a government agency. So their mechanism is different, but again, the value will be more or less similar. So for example, AQI prediction value will be more or less similar. Say sometimes 70, ours may be 80 or 81. So those kind of things are there. Again, you can try those things.
Sir, sir, since you have the practical experience of doing this, I would still like to know. So you have the IoT device, and you have integrated with the web application. What are the practical challenges that you have encountered during this process? Then how you tackled them?
The practical knowledge is the connectivity, ma'am. First, what we did is we actually used our Wi-Fi, readily available Wi-Fi. So as you all know, the Wi-Fi is actually blocked using the firewall. So automatically, any external network we cannot connect with our firewall. So that was one big practical problem which we faced, breaking this firewall. That is actually our personal problem. So in order to solve that firewall issue, what we did is we actually formed our own network, and we are using our own network to connect the cloud, to integrate the cloud with the hardware which is developed by us. And also we are using LoRa. So LoRa, another important problem is LoRa actually in theoretical perspective, LoRa is actually claiming that 4 to 5 kilometers range. But in our practical cases, maximum of 800 to 900 meter is what we got. So that network, LoRa network actually provides connectivity to 800 meters maximum. So the hardware which is placed in the visibility of that 800 meter will be connected to LoRa, and that data we can directly connect to cloud by using the chip in value. So that is one difficulty. The other difficulty which we faced was so connecting the cloud and analyzing the cloud. So and again, if you see cloud, the we are not like sometimes all these we are actually pumping our every minute data. So in every minute one data will be actually sent by these modules. So the number of data is actually huge. So later by analyzing all these data, some false data is also coming, from noise data is also coming. So all these things are actually adding to the data value. So the bill which is coming every month is actually different. Each and every month, the cloud bill which we are paying is different. So suddenly 1 month we got 7,000 rupees. All the other months we had 3 to 4,000. So when we checked it, some raw data is also coming, some kind of noise data is also coming, some equipment was fault. So again, even though it is false, it is sending data. So this made us to keep a check on the data which is pushed from that particular hardware. So these things were some of the practical problems which we faced. And again, problems will be there when you implement such systems in practical scenario. But the thing is, you need to identify what was the exact problem and to come up with a solution. And again, to come up with a solution will not be easy. So we have to trial and error. So you have to do the trial and error method. Which one suits best? We have to adopt that particular strategy.
Okay, thank you, sir. I'm trying to learn from you. Sir, you had a subscription. No, you have taken the subscription of cloud. When
Yes,
we
ma'am.
take the subscription, what are things that we have to look into it?
To
No.
get the cloud subscription, no, like only we have to register in that, and we can opt for prepaid and postpaid. So we have opt for postpaid kind of thing, and the bill will come, and we are paying for what data we have consumed, what data we have used, or what space we have used. So again, different kinds of platforms are there. So we have used AWS, and
Okay. So you use cloud only for storage.
analysis also done, ma'am. Our machine
Okay.
learning algorithms are running in the cloud itself.
So you are not taking those services.
Yeah, we have
No,
taken those
you are doing
services
that.
also.
Okay.
Cloud storage and also for storage. Again, for storage, if you means we have a physical server also. But again, as you told, there are so many practical difficulties in syncing our physical server with the IoT hardware. So that API is not getting connected. So that physical server was actually waste. So we thought, instead of physical server, why can't we go with the cloud? So cloud was a bit more easier than the connecting with the physical server. So we thought we'll store the data in cloud itself.
Okay. Thank you, sir. Thank you. Thank you
Okay,
for generously sharing all your experiences, providing
all
the
these
details.
things. Actually, it's not my own work. As I told, there is a team behind this. All these people, I'll show you. These people are doing it. They are actually sharing with me. They are making me understand how they have done, how we are doing. We will be discussing all these things, and we will be coming up with solutions. So this is the team behind all this work. So I appreciate
Obviously,
their
it's a
hard work
teamwork.
and
Yes.
sincerity. Yes, ma'am. Okay.
Thank you, sir. Thank you, sir.
Okay, ma'am. Thank you.
Thank you very much, sir. The session was
Thank you.
very beneficial to all the participants. Dear participants, we'll take a 10 minutes break and we'll meet again at 7:30. Thank you. Good evening, everyone. Once again, welcome to the fifth day and to the second session of the fifth day. The second technical session of the fifth day for the sixth day ATAL sponsored online faculty development program on advancements in cloud and edge computing research and industry perspectives. The second session focuses on an advanced and application oriented topic, edge IoT integration, which highlights how edge computing enhances IoT systems by improving latency, scalability, and real time intelligence. It gives me great pleasure to introduce our second resource person for the day, Dr. Ragesh GK, Associate Dean, Industry Relations and Fundings at Indian Institute of Information Technology, Kottayam. Sir brings with him strong experience in academia industry collaboration and applied research. His session will provide valuable insights into practical strategies and real world use cases of integrating IoT with edge computing. Sir, we are truly honored to have you with us. I kindly invite you to take over the session and share your expertise on edge IoT integration. Thank you, and over to you, sir.
Yes, so thank you for the kind introduction and hope I'm audible to everyone.
Yes, sir, you're audible, sir.
Okay, since I'm not using any external, mic or something, I hope my voice is clear and evident, right?
Yes, sir, your voice is also
Okay.
clear.
Okay, thank you. So good evening, everyone, and thank you for.
Welcome.
Yeah, good evening, Remini ma'am. Yeah.
Yes.
So thank you, Dr. Remini ma'am and the organizing team for inviting me to take a session as a part of this ATAL sponsored faculty development program on advancements in cloud and edge computing. Okay. And I'm happy to be associated with Adi Shankara again because many long years I spent there at Adi Shankara as assistant, associate, professor, and HOD of electronics department. And by 2021 only, I moved from Adi Shankara to IIIT Kottayam. So currently, my area of expertise is in Internet of Things, wireless communication, and I'm having two labs here, primarily focusing on drone technologies and also like idea to market kind of products development, etc. Okay, so coming to today's topic of discussion, Dr. Ajay has already given you a level of understanding on Internet of Things, how IoT is being clubbed with cloud computing and other underlying communication infrastructures. So nowadays, you know that this IoT or any other kind of technology, they are not actually working on a standalone manner. It's an amalgamation of different technologies for different use cases. So here today in this talk, I'm going to give you some insights, my experiences, and some research directions, especially on a topic like edge intelligence, which is again clubbed with IoT data, and it should have again a strong infrastructure to make it sense. So that's why I clubbed IoT with 6G or another cellular infrastructure technology, which has to be there to provide the actual meaning for edge intelligence. So I will be talking more on edge computing and all, but it's more about edge intelligence. So that's why the topic title is slightly modified into edge intelligence for IoT and 6G convergence. Here we'll be talking more about architectures, different optimization techniques and future research directions. So this is the overview of this particular session. So we know that, so we will be starting with the motivation for edge intelligence in large scale IoT as well as 6G communication systems. Next, I will be moving on to different associative or related technologies of edge intelligence, like edge computing, federated learning, and AI model optimization. And we will be also touching on the key challenges here, like the privacy, security, different resource constraints and scalability. And other parts like definition of, that will be second time. Like after motivation, we'll be going to the definition of edge intelligence, comparison studies and all. And I will also be talking about how this edge intelligence is connected with IoT and different cyber physical systems and 6G as the backbone communication network. And finally, we end up this presentation with, we have a discussion on research and roadmap and future directions for AI assisted or AI native 6G edge systems. Okay, so we all know that over the last decade, we have witnessed a lot of advancements or a lot of disruptions happening in the connected devices technology with the advancements happening in sensors as well as in other intelligent systems. And the IoT or the Internet of Things, which has moved far beyond you called a simple data collection kind of a technology, because it now is the backbone for many critical infrastructure. You know that IoT itself paved the way for different automations, especially our Industry 4.0 or many other autonomous systems, especially in autonomous vehicles and all. Lot rapid technology disruptions happen because of the advancements happening in the sensor industry, as well as the IoT ecosystem as a whole. And also we moved to smart healthcare because of this. We moved to intelligent transportation because of this. And also a lot of, as I was also hearing to what Ajay was mentioning in his PPT on last few slides about the environmental monitoring project that they are doing. So there also we can find a lot of, like involvement of this edge intelligence and IoT, etc. So similarly, in if you take a wireless communication, systems as a whole, they're also undergoing a lot of fundamental, transformations. So as we nowadays, the talk of the town itself is about the 5G, all right, and we are now doing a lot of research and activities, and the government has a lot of initiatives in the Bharat 6G vision and all. So nowadays, networks are no longer designed just to transfer data. As you might be knowing, like about the evolution of different communication networks. It started with the 1G and we are now marching towards 6G. And the earlier generations before 5G, we know that majority of them are just for transporting data from one point to another. But with the introduction of 5G and 6G, it is not about a mere cellular network. It is all about an underlying fabric, an underlying, intelligent fabric where you can have different levels of use cases meeting the demands of different users. Someone will be looking for reliability, someone will be looking for throughput, someone will be looking for data speed, yes, because that ultra reliable, low latency kind of communication, etc. So we move beyond this 5G and marching towards 6G networks, and these networks from 5G onwards or 5G and beyond networks are not designed for just transporting data from one point to another. Instead, they're actually evolving into more intelligent platforms capable of doing a lot of sensing. They can learn by itself, they can adapt to situations, they're context aware, and they could provide you some intelligent decision making, right? So that you can convert all those decisions into some business outcomes. So this convergence of massive, IoT deployments or the next generation kind of communication networks raises a critical question. What is the question? Like how we are going to process this large volume of data. We nowadays call it as a big data, right? Because nowadays it's all about massive IoT because the number of devices generating this data is enormous. Now itself, you can know that according to NASCO, every Indian, they're having at least 7 devices always connected to internet. They're all generating data. So how do we process all this data? How we are going to analyze this data, and what kind of action, or what kind of action that we can do on this data? But whenever we do some kind of process analyzing or acting upon such kind of enormous volumes of data, the question is, can we do it in a reliable basis? Can we do it on a secure basis? And can we do it in a real-time basis? Even if it is not real-time, there is no point of saying it's an autonomous system. Autonomous system, the word itself is embedded with real time. So if it is not doing any kind of real time activity in a reliable, secure fashion, then that technology or that product that we are building is no more. We cannot name it as an autonomous system, right? So traditional cloud-centric computing that already Ajay has mentioned, I hope he has mentioned some computing models and on. So these traditional cloud computing or cloud-centric computing models are increasingly insufficient to meet these kind of large volumes of data. Because majority of those cloud computing models that we are discussing are centralized in nature. Centralized processing are happening, right? Centralized processing, and you know that what are the benefits that this centralized processing will give you, and what are all the demerits, right? So one of those things, whenever we talk about this centralized processing, you need to think about, these kind of infrastructures will introduce things like latency. It will create, bandwidth kind of bottlenecks, because we are talking about wireless. I do understand that IoT is not always wireless, but 95% of the IoT communications are happening in wireless. So majority of these communications, since it is happening in wireless, they're all battery constrained. So we need to think about the bandwidth bottlenecks. We need to think about latency. We think about privacy concerns, because we are putting our private data on the cloud, and we are more bothered about whether, if it is healthcare data, if it's a financial data, people more care about those kinds of sensitive data if it is stored somewhere away from the consumer side. So create some kind of bandwidth bottlenecks, creates a level of, it raises a level of privacy concerns, and also it limits scalability. So especially so all these kind of, what is that? These constraints are there for majority of the real time. These are the major concerns for many mission critical, applications, latency sensitive, mission critical applications. So this is where edge intelligence comes in, or edge intelligence emerges as a transformative paradigm. So it is a transformative thing. We are not actually replacing cloud computing with edge computing. We are now going for extended capabilities of cloud towards the edge side. So these edge sides will create a transformative paradigm. How? Because this edge intelligence moves the artificial intelligence and decision making very much closer to the data source side. So data source side, so that you will be more prepared for this kind of real-time perception. It will provide you, it will enable you with real-time perception. It will give you, you can learn. Learning happens there, and controlling happens at the network edge. So in parallel, when we take this notion of edge intelligence into 6G, we know that 6G introduces the capabilities. So why we are moving from 5G, 6G and on? Not only for data speed and on. It's not about how much data speed that you're getting out of the 6G. Even though the evolution of these cellular communication networks will give you better data rate, that is not the prime purpose. Okay, so the first capability, obviously, it's a ultra low latency. And second thing is the massive connectivity. These kind of devices, almost all devices, all gadgets now we are using are all connected. They're generating data by itself. And also, when we move from 5G to 6G, 6G have a better vision now, because we are going for integrating different terrestrial and non-terrestrial networks here. And so that when our notion of just connecting devices is become larger, that notion becomes wider, broader, then we need to have an external intelligence in place. So the AI native communications, AI is the core of 6G. You can look into that 6G architecture and see that AI is at the core. Without AI, there is no 6G. So so that's why it is AI native. Normally people will call 6G as AI native 6G. So it's AI native communication. They're non-integrated terrestrial and non-terrestrial communication networks all together will create the ideal foundation for a distributed data intelligence. So in today's talk, in this session, I will try to explore, how this edge intelligence acts as a key enabler for the convergence of IoT and 6G. And we will also examine some mainstream architectures, as I told you in this overview. And also we look into the emerging technologies in AI, as well as what are the challenges and open research directions. Okay. So let us begin with the fundamental question, like why this edge intelligence and why this discussion. So let us begin with this fundamental question of why do we need edge intelligence at all, right? So for many years we know that whenever we discuss about these cloud computing infrastructures, artificial intelligence or AI has been primarily cloud centric. It's not edge-centric in its naive way. It's a cloud-centric one. So data generated by all these kinds of massive IoT devices, they're all transmitting these collected data into some centralized data center. And all these data is being processed there itself in the centralized data center. And the results or the feedback are sent back, right? That is what is called as, in all together, we can call it a cyber physical system. So this model actually works reasonably well. Okay, cloud-centric AI model will be reasonably very well. It is good for delay-tolerant applications, not latency-sensitive applications. Delay-tolerant applications, that is fine. But it breaks down completely for, latency-critical applications, or when we take any kind of privacy sensitive use cases, then this cloud-centric AI intelligence will fail. Okay, two things. The one is it won't work for delay sensitive applications, for latency critical applications, and for privacy sensitive use cases, because data sovereignty is not maintained in cloud-centric networks. Okay, so that's why you can take different kinds of healthcare setups. Even though in India also witnessed many such kind of agreements with the US about transferring our data to US cloud centers, and people in Kerala, they protested a lot for that because about data privacy. So consider that you can take, so whenever we are bothering about this latency sensitive or privacy sensitive use cases, immediately we have many kind of things coming to our mind. The first thing will be about, we were discussing about autonomous cars nowadays, autonomous vehicles. So consider applications such as autonomous driving or remote healthcare monitoring, or as I said about Industry 4.0 or smart factories, or about any other kind of, public safety systems. In all these kinds of use cases, that even a very few milliseconds of delay, can lead to incorrect kind of decisions, or it will produce some kind of unsafe outcomes. So sending data to a distant cloud and waiting for a response from the cloud simply is not acceptable in these kinds of latency sensitive, privacy preserving kind of use cases, right? We cannot wait, because that whenever we are generating a data from one point, it will take some, for example, time T1 for generating of data, time T2 for sending this data from the cloud, from the data originating side to the cloud. Then processing will take another time, say T3, and sending a feedback back to back to the originating side, again T4. So it will be hardly taking some T1 plus T2 plus T3 plus T4 is the total time for processing, getting the data and processing it and getting a feedback and generating an outcome. So these kind of delay is not tolerable in privacy sensitive applications or latency sensitive applications like autonomous cars, autonomous vehicles, autonomous driving, smart healthcare, smart factories, etc. So in all these cases, that we need split fraction second decisions. Even a few milliseconds of delay can lead to some incorrect, unsafe kind of, outputs or outcomes will be generated out of that. So sending data to a distant cloud and waiting for response is not at all acceptable in these kind of use cases. But at the same time, that the scale of IoT, the scale of IoT deployments is also, going in an exploratory manner, right? It is exploding like anything. So billions of sensors are available now. You know that because majority of the institutions now, they're having IoT labs. They're all working on different use cases. Even Adi Shankar is also working on an IoT kind of a big project from IT about environmental monitoring and, about near the Karadi area and all, Periyar River basins and all. So billions of sensors and devices are like the same scenario, like continuously generating massive amounts of data. And, just backhauling of all these kind of raw data, to the cloud is not only, inefficient, but at the same time, it also, places an enormous burden. It is like a cloud burden and all the kind of stuff, all the kind of data stuff we are pushing the data to the cloud. So we are actually overburdening the cloud like anything, and it is overburdening the bandwidth and infrastructure. But now with the emergence of these kind of intelligent cellular communication technologies like 5G, 6G and all, the expectations are more even, very, very stringent. So that's why every cellular, evolution takes some 10 years. You know that 2020 5G came. Now we are expecting 6G in 2030 because 10 years of time is needed for such kind of an evolution. And the same thing happens for 4G, 3G, 2G and all. So with the emergence of 6G, we are having as a customer, as a provider and all, we are having more expectations on such kind of technologies. So 6G applications require more. It is more for real-time autonomous applications where ultra low extreme latency is expected, extreme high reliability is expected, and intelligence must operate at the same time scale as as with respect to that of the physical processes. So fortunately, we have these kind of edge devices today, and they are no longer, it is no longer like a simple, say like a sensing unit. They are equipped with significant computational capabilities, including, about the AI accelerators, and they could make some, local inferences, where there is inferences from the data generation side itself without moving away from the data generation side. So that, it makes those decisions very local so that finally the users, the data consumers or data owners, they have that privacy thing, they have the trust thing comes in when they are storing everything on the edge side. So privacy regulations and trust considerations, etc., is, it is being preserved with the help of this edge computing. So all these factors together, all these kinds of factors, what we have discussed together, make this edge intelligence not just an optimization of the existing systems, but this is the need of the hour, need of that architectural shift from the older 4G or the mere kind of sensing equipments to more intelligent, more futuristic kind of IoT integrated 6G networks. So this naturally leads to, the next question that is being answered in the next slide. That is what exactly do we need, or what is exactly this edge intelligence? So now we understand. So the why part we have finished in the first slide, why part. So let us clearly define what exactly this edge intelligence means. So this edge intelligence, that it refers to the deployment of your artificial intelligence algorithms directly at the network edge. That is, when I am saying at the network edge, I don't mean that it is on the device itself. It could be near the device also. Okay, on the device or near the device where data is generated. But we know that from the traditional, data center architectures and all, we know that everything is being forwarded to cloud for processing, but edge intelligence data is actually processed locally, and decisions are actually made very much closer to the data generation side. So this kind of, a shift significantly reduces, as I told earlier, like it significantly reduces the latency, because data no longer needs to travel back and forth many times. So distant travel, those things can be avoided. And also it also, significantly reduces latency, also that bandwidth consumption and other kinds of, resource preservations, etc. Because everything that model up, the majority of those data processing will be happening at the edge itself. And we are just forwarding, some kind of model updates, kind of thing, some relevant, many only relevant information, or some kind of relevant insights or some model updates are only transmitted instead of these raw data streams to the cloud. Okay. So another key advantage I told you about the privacy. So sensitive data, because majority of the edge computing infrastructures, if you see in literature as well as in companies like Siemens or Bosch and all, you can see that all those infrastructures are mainly into these kind of, patient related or person related kind of informations, because these are all, sensitive data such as the health information or location information or personal informations or some, some parameters. So such kind of local parameters, etc., will be like, will be exposed to something like it will be opening the back doors for attackers to do some kind of malicious activities. So that's why everything is being preserved on the edge side. Okay, and majority, so most importantly, that nowadays we are talking about the context aware things, right? Context aware. So edge intelligence actually enables the kind of, the real time and context aware kind of intelligent services. So decisions can be made immediately, like, whenever we are telling about these autonomous cars and all, you need to apply the automatic braking, right? Whenever a pedestrian is crossing the road, the dashboard the dashboard inside that car has to take decision by itself on a split fraction second without forwarding the data to the cloud and wait for some commands from the cloud. It is not permissible at all in such situations. So decisions has to be made based on local conditions, which is very much critical for applications such as these autonomous systems or any kind of whether we call it a smart infrastructure. Okay, so I can tell you in simple terms that edge intelligence now brings the brain of those, brain of system very much closer to this kind of, data generation side or consumers or the data owner side. So here in this figure, you can see that on the top, it is all about the evolution from the cloud computing and finally it reaches the edge intelligence, right? It starts from cloud computing to edge computing and then finally reaches the edge intelligence. So at the top, you can see the Netflix, the AWS, the Google Cloud and YouTube and all those things. So we have many centralized cloud platforms available. So some examples have been highlighted there, like AWS, Azure, Google Cloud, etc. And these offer high computational power. We know that how Netflix uses anything, not only Netflix. Ajay was telling about this kind of cloud infrastructures like Microsoft Azure or Google Cloud, etc. So these offer, even though these offer like high computational power, but they're all very much far away from the end users, right? So this also resulting in what we called as latency and bandwidth overhead. So here in the middle layer, you can see the middle layer where represents the edge computing, where computation is pushed closer to the users, through some base stations and the edge nodes, right? So this reduces latency, but you should understand that even though it reduces latency, but it mainly focusing on data processing and rather than intelligence. So that's why we have two branches, edge computing and edge intelligence. Edge computing is more into like how processing has to be done. There is nothing, the edge computing devices has nothing to do with intelligence. So that's why this, even though it reduces latency, but it mainly focusing on data processing rather than running an intelligence thing on the edge side. So at the bottom, you can see different kinds of end devices, such as different smartphones. You can see their sensors are there, vehicles are there, that are continuously generating real-time data. And edge intelligence goes actually a step further by embedding this AI-driven decision making at the edge, enabling real-time, context-aware, privacy-preserving intelligence services. Okay. So moving on, so we have this evolution from cloud computing to edge intelligence. Right, so you can see here the low latency. So it started from 1990, where we have the content delivery networks came. Then in early 2000, we moved to the peer-to-peer kind of communication networks. And the early 2010, we moved into our micro data centers were introduced, and 2020 we talked about, and many of the applications have been moved to the edge computing. So to make you understand edge intelligence more, more in depth. So this will help to look at how computing paradigms have evolved over time from 1990 to 2020. So we began with some traditional cloud computing, where data generated by end devices is transmitted to centralized data centers for processing and decision making. And this model, that this kind of a model offers a lot of scalability, right? Scalability and many powerful computational features came. But ultimately, we can see that when we move towards this kind of, automation kind of thing, then it introduces latency issues, bandwidth overhead issues, and privacy concerns, right? So as I told you, like, when we are saying that as we move from, as we, one second. Sorry, mouse and, okay. So as applications, as applications became more interactive, that's what, that we more interactive, and there is a rapid, the increasing of data volumes because of this massive devices, edge computing emerged. Okay, again, emphasizing the importance of edge computing, migrating from the early content delivery services, and now we have, edge intelligence in place. That's it. So here again, there is because many of the times we interchangeably use edge intelligence with edge computing, and sometimes with cloud computing as well. So at this point, it is, having some issues with the mouse. Second. Okay, so at this point, it is important to clearly distinguish how this edge intelligence from, the traditional cloud computing and edge computing, as these terms, as I said, like, as we are using these terms often interchangeably. So this figure you can see here, this figure compares that on device intelligence with edge intelligence and cloud intelligence across different key performance dimensions like privacy, latency, diversity, scalability, on-device cost, and reliability. So on-device intelligence, what is that? On-device intelligence means, that it offers some strong privacy and low latency. But at the same time, even though it provides strong privacy and low latency, it is limited in scalability, right? Because model diversity is missing here or limited in scalability because of the resource constraints. Because it is all about on-device intelligence. So there will be a limitations on scalability side as well as on model diversity side due to the resource constraints. So when we talk about the cloud intelligence, so cloud intelligence, it provides high scalability, and there is a room for, there is a model diversity available, but again, it suffers from, say, like high reliability and higher communication cost and weaker privacy. Okay, so when we move from cloud intelligence to edge intelligence, it lies between these two extremes. That is achieving, so there is a kind of I can say that it's a balanced kind of trade-off. So edge intelligence has to lie between these two extremes of on-device intelligence and cloud intelligence so that it could achieve a balanced, balanced trade-off. That is, when I'm saying balanced trade-off, it significantly reduces latency and it improves the privacy compared to the cloud while still offering a better scalability and reliability. Okay, so overall, the entire figure highlights or tells us, the importance of edge intelligence or edge intelligence, how this edge intelligence is more practical compared to the cloud and on-device, intelligence, and how it provides a balanced solution. How this edge intelligence provides a balanced solution for real-time, scalable, and privacy-aware intelligent systems. Okay. So now we move to this, the next, we talk about what are the key enabling technologies of edge intelligence. So till now, we have seen that why edge intelligence provides the best balanced kind of solution. Now let us have a look at, what are the key enablers for that. So the first and foremost or the most fundamental component here is edge computing infrastructure itself. Without edge computing infrastructure, we cannot think about the edge intelligence, right? So when I'm saying, when we are describing this edge computing infrastructure, so these are all the, different components or these are the backbones of any edge infrastructure. That is, it consists of different edge servers. It consists of different edge gateways. It consists of different base stations and also different micro, the data centers, which are actually all these things, all the edge servers, gateways, base stations, micro data centers, etc., are deployed where? In edge computing, they're all edge infrastructure, they're all deployed very much close to the user. And these provide the computational foundation for running different kinds of AI models outside of the cloud. So that's why I told you in the beginning, we are actually extending the capabilities of cloud. It's an elastic thing, right? We are actually extending or bringing or pushing the capabilities of cloud towards the edge side. So that's why on top of this infrastructure, you can see that many artificial intelligence and machine learning algorithms will be deployed. I'm not saying that even heavy AI or ML models can run on edge devices, but there are limitations. That's why, but even if depending upon the user scenarios, some of those models and applications can still run on edge side. So these models, these edge-centric models perform tasks such as, the first thing is perception. And second thing is prediction. And the third thing is after prediction, it's all about decision making, right? Decision making all together, all the operations, perception, prediction, and decision making, everything happen at the edge, enabling these real-time responses. And you can say that nowadays people, even my research scholars, are also working on different federated learning algorithms. So federated learning, we know that federated learning has a lot of scope in healthcare data, right? Healthcare data sharing. So whenever, many hospitals are, working on a single project, they do not want to share those private sensitive data. So these kind of federated learning actually plays a crucial role in such kind of collaborative model training across different distributed edge devices. Why? Because in federated learning, we are not actually sharing the raw data itself. So this is very much particularly important for such kind of privacy sensitive applications. So IoT devices here act as just like a data sources, continuously generating these kind of real world, information. You can take the example of a W band, a wireless body sensor network, and all. From there, a lot of healthcare data is being generated. So these sensors, even though it is not about sensors, the body sensors alone, you can take the example of surveillance cameras as well. Nowadays, in Indian roads, you can find a lot of surveillance cameras, and they're taking some edge intelligence by understanding, whether the vehicle is moving at a lot higher speed or not, speed limiters and all those things. So cameras, they're also data generators, and also different kinds of these generators will provide you some actions with the help of actuators. So without reliable sensing or edge intelligence, edge intelligence or edge computing infrastructure will fail. So we should have a reliable sensing, then only edge intelligence can function in a reliable manner. So high speed and low latency communication technologies like our 5G or 6G kind of a very good supporting communication infrastructure have to connect these kind of devices, edge nodes, as well as with the cloud. So these networks ensures that intelligence can be distributed at the same time it can be coordinated efficiently. Okay, so in these kind of key enabling technologies like 5G, 6G, federated learnings, or any kind of actuators, sensors, etc., all these. So we can say we can see that it is a tight integration of all the different levels of technologies that makes this edge intelligence more, more practical, possible, scalable, and effective. Right. So that's why nowadays we all say, like, whenever there's an IoT, normally people will say like it's a cloud assisted IoT. It's not just IoT, it's a cloud assisted IoT, or people will say that AI IoT, that is artificial intelligence enabled IoT, right? So that's why two different technologies are now tightly integrated so that we can have a better ecosystem, right? So now you can see this is one of the interesting papers I did. Sorry that I didn't mention that paper name over here, but I can share you through your organizers. This is a paper, latest research paper published in IEEE Communication Surveys and Tutorials, where the entire paper is all about how we can integrate edge with 6G and IoT. So from that paper only, I grabbed this particular a comparison table among different edge intelligence, edge computing, and cloud computing. So this comparison, you can see that different features have been listed over there, starting with computation location, latency, processing, resource capability, security and privacy, etc. So this comparison is particularly important from a research perspective, because as it highlights how the focus shift across cloud computing, edge computing, and edge intelligence. So cloud computing, that it reaches traditionally emphasizing the scalability, the scalable architectures and all, high performance computing, resource management, and handling different levels of complex, computation incentive, compute incentive kind of workloads, etc., in a centralized environment. So edge computing research moves that focus towards a decentralized or a distributed kind of environment where it is giving a lot of importance for a low latency kind of architectures, task offloading, and efficient coordination between different edge nodes as well as with the cloud. So this particular comparison table gives you more understanding about how this edge intelligence represents a strong research shift towards an embedding kind of AI and machine learning in a resource constrained environment. Why I'm saying resource constrained? Because you know that you can take the case of nowadays we are talking more about drones or flying IoTs. So flying IoTs, you know that these drones are also like edge devices, right? Majority of now the drones are autonomous in nature. Now we are actually developing a drone, which is a indigenous kind of flight controller without GPS. Without GPS, a GPS denied environment, we are leveraging technologies like SLAM. We are leveraging technology sensors like that lidar, etc. for making so that these drones or the unmanned aerial vehicles have a smooth operations in an indoor environment first. Then we will be extending that capability to the external environment. For the time being, it is been research been happening in the indoor environments. So there also we are actually doing we are giving intelligence to the drone to take some decisions by itself. Okay, so so there are different use cases for that. So this kind of a comparison table actually tells you about how this edge intelligence represents a strong candidate in supporting such kind of use cases, with some key challenges also. There are some key challenges also, including the resource constraint, because prawns and all, you know that we have some limited memory capacity, or even if we are using boards like Raspberry Pi or Jetson Nano or Jetson Orin kind of boards, etc., it has many limitations, right? So there are different resource constraint limitations available, but again, we are going with such kind of things for autonomous decision making. Yeah, any questions in between? I heard some noise in between, so that's fine. Any question?
Sir, I thought of asking at the end. Shall I?
Okay, sure. You can, please. Yeah, go ahead. If you have any question, no problem. Okay, no problem. So if you're asking at the end, can I continue? Shall I continue? Shall I continue?
Yes, yes, sir.
Okay.
Sir, one communication in your chat window. Could you?
Actually, I'm just saying my what is that communication?
Okay. Then we can take the questions at the end. That would be.
You can ask me. You can just read
No,
it for
I
me.
have seen one
answer it.
question I have a question that I'll ask at the end, but that's a question in the chat window that we can take it at the end. That's fine, sir.
Okay. Yeah. So here the current research, if you ask me about the current research happening in the edge intelligence, you know that nowadays, since we are actually extending the capabilities of cloud towards the edge, the researchers are now working on lightweight models. Even in my case, I have a funded project from C3 iHub of IIT Kanpur, where we are doing a project on secure UAV, multi-layer secure UAV. We are actually providing security at the physical, data link, and application layers. So in physical layer approach, what we are doing is we are trying to defend different kinds of jamming attacks. Okay, and for that, different use cases that we are doing, like drone-to-drone communication, drone to ground station communication, as well as a spam communication. So how it can defend these kinds of attacks. And we are actually working on different, secure NOMA, that is non-orthogonal multiple access kind of technologies, especially in the physical layer, to defend such kind of attacks. Again, AI has a huge role to play there. But again, this is one of those works that we are currently doing. For that, we need some kind of lightweight cryptographic models to work on the physical layer. Because we are not actually we are not running those models in a downstation server. We have to run those models in the drone itself on some, as I said earlier about the kind of boards that we're using, like Jetson Nano or Jetson Orin or kind of similar kind of boards. So there we need to explore different kinds of lightweight models. We need to incorporate machine learning, like federated learning algorithms over there. We need to have some kind of online learning. Online learning should be there. And majority of the time, since this is drones and they are using for different kinds of use cases like disaster management or such kind of mission critical applications where self adaptation is needed. So we need to work on that kind of self-adaptive algorithms, especially in the edge side, that allow systems to respond intelligently in real time without relying on the cloud connectivity. So overall, this kind of evolution, one second, I'm sorry. I'm having some issues with the mouse. Okay, so here, yeah. So overall, these kinds of evolution like edge intelligence, cloud computing, then to edge computing, and then into edge intelligence. This evolution actually reflects a kind of transition in research from improving. So nowadays, people are more into designing context-aware systems rather than working on the computational power aspects. Right. Before, when people were doing, I know that because during my PhD days in 2015, that time people were more working on the cloud computing, computational power adaptation kind of thing. But now the research has been shifted from the computational power to designing more intelligent, more autonomous, and more context-aware kind of systems operating at the network edge. Okay. I think I'm going a little bit slow now. It's 8:21, spending more time on certain slides. Sorry for that. So edge intelligence and technology stack in IoT 6G. So up to this point, we have understood, we have built a conceptual understanding about edge intelligence. So now this is, it is time to move on to the core technical, framework like edge intelligence, saying like it is not at all a single technology, but it's a tightly integrated network. As I said earlier, it is a tightly integrated stack built on the top of IoT and 6G systems. So at the foundation of the stack, you know that there is edge computing are there, which provides the execution platform for running different kinds of AI models close to the data sources. But on the top of that, you can see, we can see that federated learning has a huge role to play there. Instead of collecting these raw data, centrally, models are trained collaboratively. So like my own student, Lekha, she's a PhD scholar here. She's working on federated learning on healthcare data in like incentive analysis, incentive federated learning mechanisms, and she's doing an internship as well in Aravind Eye Care Hospital in Chennai, where they're working on these kinds of patient-centric data, especially on eye diseases. So they are collaborating with the different Norway-based healthcare sectors, and for that they are actually building a federated learning architecture, a framework there that plays a critical role. So here also, why federated learning? Because instead of collecting all these data, processing data centrally, models are trained collaboratively across distributed IoT and edge devices that directly, addresses different privacy and different other kinds of policy-based or regulatory-based kind of constraints. Okay, so here, so that is why. So here you can see that majority of these models are heterogeneous in nature. Because why heterogeneous? We have different varieties of IoT devices from different manufacturers and all. They're all ranging from different capabilities, like on the resource management side or resource constraint side. So we have different heterogeneous IoT devices ranging from resource constraint sensors to different powerful edge servers. So this is why we should have an underlying strong communication infrastructure. That's why I'm just trying to club this edge computing with 6G. So 6G becomes a key enabler here. So unlike the previous generations, even 5G also, 6G is designed to support AI native communication. So if you know about 5G technology, you know that AI is not at all not have a prime role in 5G technology, right? AI is a kind of a supplementary service in 5G technology, but For 6G, it is a key player. So that's why it is a AI native communication in 6G. So which provides many ultra low latency, and there is a tight integration between this communication and computation in 6G setup. So overall, this kind of this technology stack reflects a kind of shift from isolated end systems to moreover a cross-layer kind of design. You can see that a cross-layer kind of design where intelligence is having a prominent role along with the communication and computation. Altogether, they are jointly optimized, right? Then moving from so edge computing as the execution platform for edge intelligence. Now, okay. So now let us focus on the first concrete kind of building block of edge intelligence, that is edge computing itself. So in 2025, so I have captured this slide from NASCOM website, where they have a discussion. There is a white paper available on the edge computing infrastructures. And from there, I could understand that these are the best edge computing platforms of 2025. So edge computing provides the, sorry that I'm just having some issues with my mouse. That's why going and coming and back. So edge computing actually provides the, the physical as well as the virtual execution platform on which we are actually operating the edge intelligence. So when you may be knowing it, like what this edge computing consists of, this infrastructure consists of. We have a lot of edge servers there. We have the gateways, we have the base stations, we have the different kinds of, if you're taking autonomous intelligent transportation systems, all these roadside units, your traffic controller units, etc., becomes intelligent. So roadside units also a part of this edge computing infrastructure in an intelligent transportation use case. Some different kinds of micro data centers will also be available, which are deployed close to where the data is being generated. So instead of forwarding the, as I told, the raw data into the cloud and all, these edge nodes execute the AI inference locally itself, and this allows decisions to be made within milliseconds. So these are the best edge computing platforms available, like Azure IoT Edge, even for my research as well, since my research was concentrated mainly on building secure and cryptographically enforced kind of patient health record systems, PHR, or electronic medical record systems, where we are getting all this data from different wireless body sensor networks, and all this data will be forwarding to a cloud infrastructure. That time we were not concentrating on the edge side, but we were more into the cloud side in 2015, I'm saying. So then edge, so there also sorry. So during that time, I also used my PHR system as IoT, this Microsoft Azure, because majority of the PhD works during that time, we were using this Microsoft Azure as the cloud platform. So in 2025 also, it is, I'm happy to see that since after this, many new IoT cloud computing paradigms evolved, even though Microsoft Azure IoT also itself listed as one of the best edge computing platforms. Okay, then we have the Clear Blade, where software for industry IoT applications is there, and Eclipse, IBM backed the kind of platform for enterprise scale edge applications. So edge intelligence system architecture. So here you can see that presents a high level system architecture for the edge intelligence, often referred to as the IoT edge and cloud continuum. So at the lower level, we can see that this is the device level or the device layer, where we have different sensors and controllers. So we have IoT and devices such as sensors, cameras, vehicles, wearables, etc. there at this device layer. And these devices continuously generate real-time and highly heterogeneous data, because we know that the data generated by autonomous vehicles is entirely different from a wearable health bit device, right? So these devices continuously generate real-time and highly heterogeneous data from the physical world. Directly above them are the, the edge layer, where you can see the different edge nodes, gateways, base stations, as I said, like micro data centers, etc. And these edge devices host AI models that could perform different local inferences and real-time data decision making. So by processing this data at the edge, the system significantly reduces the latency and all, and it is actually, if there is an urgent, if it is, if it is not, it cannot be processed at the edge layer, those selected data will be forwarded only to the cloud layer in order to reduce the burden, reduce the processing burden, and reduce the bandwidth burdening at the cloud layer. So the cloud layer actually still, it plays an important role here. It provides a large scale storage and global model training normally happens at the cloud layer, but but it again have a good coordination with the edge nodes. You can see that when we there is some more there is in between layer as well between the cloud and edge. We normally call it as a fog layer. Fog layer is again a layer which is again a far away from the cloud, and it has not been reached at the edge, but it is a fog. So like it is like a cloud fog and that edge computing, right? So rather than replacing everything on the cloud, here the edge intelligence enables a kind of a collaborative architecture where intelligence is distributed across different heterogeneous devices, edge nodes, as well as with the cloud. Okay. Okay, so at this point of time, do I want to answer something? Madam, if you could please read out that question, I could answer it and I can move forward.
Okay. Intelligent edge, edge intelligence, and edge computing sounds almost the same. What could be the difference between these?
That's what. Edge computing means we are actually extending the capabilities of cloud and doing those computations at the edge itself. But there is no meaning that we are running some AI algorithms there. But now what we are doing is we are actually running all these kind of AI-based algorithms at the network edge. Okay, so rather than computing, so previously, formerly, our major interest was extending the computing facilities from cloud to edge rather than putting AI at the edge. Now, after this introduction of 6G and all, which AI is at the core of 6G, we have to do a lot of intelligence to be run at the edge rather than sending data again to the cloud and doing some AI-based things at the edge and getting it back. So those things won't work in many real world applications, use cases. So that's why AI is now happening. These intelligent algorithms are running at the edge side itself. Not only computations, but the intelligence also, decision making also happening at the edge itself, rather than depending on the cloud. So that's the difference. So edge computing means we have the edge node servers, etc. We are doing the computing, all those things there, but these intelligence, the decision making is not at all a part of edge computing. So more emphasis of intelligence is that context aware or self-aware kind of networks are now building, as I told the case of drone to drone communication, whether drone has to flip, whether drone want to move forward or backward, whether it has to avoid some kind of obstacles. All this kind of intelligence has to happen at the edge side itself, rather than extending, putting those things at the ground control station. So that's why I told you edge computing is different. This is all about intelligence happening at the network edge. Okay. Whether I have answered the question or not, or do you have a different question? You can unmute your mic and ask, no problem.
Okay. It is being asked by Miss Annie Harish. No, I didn't. Okay.
Annie Harish, are you satisfied with my answer or not? Okay, so I think any answer in the chat window, ma'am? No.
No, sir. No.
Okay. Okay, then moving on. So we now move on to the role of AI ML in these edge environments. So you know that traditionally, so this could be an answer to what the attendee just asked. So traditionally, we know that these AI models were designed for centralized cloud environments with abundant, we know that a lot of computational facilities and storage facilities available. But edge environments are fundamentally different. They are all resource constrained, right? All edge devices are resource constrained. They're highly heterogeneous because all the examples like smart environments, your intelligent transportation, healthcare, factories, agriculture. So all these things, they're heterogeneous. The sensors, the equipments, the algorithms, etc., heterogeneous and operate under different dynamic network conditions. So despite of all these kind of network or the kind of device or environmental constraints, modern AI, especially like the large scale models, has demonstrated that there are having these large scale models are having remarkable kind of capabilities in pattern recognition, in learning and decision making. In this, I can quote you one example. Recently, we developed an electronic nose for Ayurvedic aroma analysis. And this was a funded project from IIT Indore under Drishti Foundation. You know that all these IITs, they are having different cyber physical system setups. They are giving fund for government, even for non-government, even UG scholars, PhD scholars, even for faculties and all for doing their research-oriented work. So likewise, we actually participated with Ayurvedic, manufacturers in Kerala. And from them, we understood that there is no benchmark system available with them to evaluate the quality of the Ayurvedic products that they're producing. So even the Ministry of Ayush don't have a benchmark system to check the quality of the Ayurvedic products. We Keralites usually have a belief that all Ayurvedic products are generally okay and they are actually safe for consumption, even though even many of the times we do not look into the expiry date of all those things. So we developed a kind of, the what is that? An electronic nose, an artificial nose for evaluating the quality of different Ayurvedic compositions. So you may be knowing that many of the Ayurvedic compositions will produce, for produce a lot of gas. Means it emits gas. And these gases can be, sensed using different kinds of sensors like metal oxide, MOX sensors. Okay, so we built actually 16 array of sensors, and these sensors can capture all these gas emitting. I'm not saying all Ayurvedic herbs and plants and compositions can emit gas, but majority of them can emit gas. Okay, because the majority of those compositions will consist of herbal things like tulsi, ginger, and all those things, and majority of them emit gases. And metal oxide, most sensors can detect all these gases and can produce some kind of patterns. So we convert all these kinds of sensitive data into different kinds of patterns, but it was just like supervised learning kind of algorithm we have used there. Okay, and because we already labeled it mainly, which are all the good products and which are the bad products and all. And from that, we have a reference model and we compare different products patterns with the reference model. And we arrived at a conclusion after some 10,000, 20,000 kind of sampling we done. And we finally arrived, in between AIMS Delhi as well came in between to check the product quality. It means the prototype that we developed, the quality and all. We went to AIMS Delhi for the product exhibition. And we got some good feedback from the doctors and even from the director of AIMS Delhi. So they actually, so initial case, we got an accuracy of some 72 to 75%. But when we submitted, we got a TRL level 7 product and it's already patented. Technology readiness level 7, it is market ready and it is being used by Vaidyanathan Foundation. which is in Ullur in Thrissur. They are actually in a pilot study now. So why I am mentioning all this means this device is not actually connected to any kind of cloud computing to have an analysis and all. But we know that these small devices, even the device that we developed is only can handle only 1 to 2 kind of mini, like minimum sized bottles of these compositions. So it can be extended to some conveyor belt kind of thing, but for the time being, it's a prototype. So not prototype, it's like consumer ready, but it can handle up to 2 different kinds of medium sized bottles. It is giving under ambient temperature. So it provides kind of patterns and all, and it is nowhere contacting with any cloud, and there is no Wi-Fi enabled kind of thing. It's everything happens at the constrained device itself. So that's why I told you these kinds of modern AI models, even though they are remarkable in pattern recognition, learning, and decision making. So if we are deploying such kind of if we are deploying such kind of large scale models in these kind of modern enterprise kind of environments, so it provides so sometimes I'm not saying the case of this electronic nose or artificial nose, but sometimes when we are extending such kind of models to the edge, sometimes we feel like it is impractical because of the latency or memory or some other kind of energy. Energy is also important here, right? Because these are all energy constrained devices, so energy limitations are there. So these limitations actually necessitate, it actually tells us all the researchers who are working in such environments to go for new approaches where you can have some model downsizing, that large scale model to a more convenient kind of simple model downsizing. So we have different kinds of architectures now available. One of those architectures is NAS. Have you heard about it? NAS? NAS means this neural architectural search, which plays a critical role by automatically discovering the model architectures that balances performances with computational cost. So through NAS also, like intelligence can be systematically adapted to different kinds of edge environments, transcending traditional kind of manual based designs to more efficient based edge deployments. Okay. Then we are moving then to the adaptive, federated, and autonomous edge intelligence. So adaptive intelligence, it is what to say. Adaptive intelligence, it adjusts complexity at this runtime. Whenever we are going in a runtime environment, this adaptive kind of intelligence always layers some adjust the complexity. So knowledge distillation also here, the knowledge distillation also enables a kind of lightweight yet capable kind of models. So federated edge intelligence supports such kind of, I told you about whenever we are going for a collaborative model, privacy preserving can be, so that's why federated learning is most preferred for such kind of, sensitive kind of data sharing networks. Okay. So I'm just rushing and moving because now it's 8:45. So then the next model is the AI model deployment across heterogeneous IoT devices. So once these kind of models are trained, we often use different machine learning algorithms, especially these kind of federated learning algorithms. This is the next major challenge, because in deploying such kind of federated learning in different edge environments along with IoT. So we know that unlike these kind of cloud data centers, IoT and edge systems are highly heterogeneous. Devices come with different levels of capacity. For example, the processing power will be different. They're having different memory capacity. They're having different energy availability, and that different manufacturers, for example, Siemens and Bosch, For example, they're all working on healthcare sector. So nowadays, we are actually working on something called a digital twin for healthcare, especially along with the Amala Hospital in Thrissur, as well as with Malabar Cancer Center in Kannur. So they are along with other parties like CDAC, Trivandrum and all. So here, there also, you can see that, these manufacturers, it's Siemens as well as Bosch and all, they have their own different hardware in architectures. They're all different in processing power, memory capacity, energy availability, etc. So we need, so what I'm trying to say is a simple kind of, if you take a simple kind of sensor node itself may have only very few, very few megabytes of memory, while the edge server, the base station may have that kind of a GPU kind of acceleration. So deploying the same AI model across all these kinds of devices is not possible. So this kind of heterogeneity actually have a huge impact on this edge intelligence, because AI models must be carefully adapted to the capabilities of each device. So that's why I told you in the introductory slides that we cannot do all the kind of AI models in a particular use case. Depending upon the use case, we are actually extending the capabilities of cloud so that we don't want to overburden the cloud with mere raw data, right? So this heterogeneity actually indirectly impacts the edge intelligence, and that's why we need to look forward to have different AI models that could be adapted to the depending upon the capabilities of different edge devices. So when we go for these kind of large, the complex models and all, that could be working very well in the cloud computing setup, but we need to have a lighter models of such kind of AI algorithms to run at the edge. So without having a proper adaptation, this model deployment can lead to this kind of excessive kind of latency or energy drain. So that's why we are having energy aware kind of algorithms has to be there, or even it can bring some unforeseen situations like system failures. So this kind of, therefore, I'm trying to say that, effective edge intelligence systems must consider these kinds of device heterogeneity as a first-class design constraint. And if you people are looking of a secure system design, security is also a part of this edge, because majority of these kinds of sensor devices are lacking inbuilt security. We know that these sensor devices are very much, for example, I'm saying these sensor devices are very cheap and they come with very minimal level of security, sometimes no security at all. And they come with some weak passwords as well. So that's why now researchers, majority of the cybersecurity researchers, if they're interested in the hardware side, they're working on certain lightweight cryptographic models, along with, whether the system by design, secure system by design, to defend attacks like timing attacks, power attacks, as well as the other kind of side channel attacks. So effective edge intelligence systems must consider such kind of device heterogeneity as a first class, as an important design aspect. And this is one of the constraints, and it should, and nowadays, very few researchers are working on that secure system by design. So this challenge, this can be considered as one of the challenges that motivates many of the researchers to work on different optimization techniques that we will be discussing in the coming slides. So here, so to make these kind of edge intelligence optimization more practical, we cannot rely on different isolated optimizations, right? As I told you, we cannot rely on isolated optimizations. Then what we have to do? Instead, this kind of edge intelligence requires more systematic, more multidimensional kind of optimization approach. What do you mean by multidimensional approach here? So here, the first dimension should be the task offloading. The first dimension should be the task offloading, where each intelligent task must decide whether it should run on the device at the edge or it has to be forwarded to the cloud. So this decision depends on factors such as latency constraints, factors such as computational load, as well as the availability of the resources which is there with the edge side. And the second dimension is the network coordination. What is network coordination? Here, we know that different edge intelligence systems are there. They are operating under different varying network conditions. So we have to look into the efficient usage of bandwidth, latency aware kind of routing, latency aware kind of scheduling mechanisms and coordination mechanisms. I mean, different edge nodes are essential to maintain a real-time real-time performance. So the third important dimension is the AI algorithm itself. So we have to work on different AI algorithm optimization, where the models must be adapted to different edge environments through techniques like simplification techniques, restructuring kind of techniques, or sometimes we go for some partial execution kind of techniques across multiple devices or nodes. And the fourth and one of the most important kind of dimension in this kind of an environment is the energy efficiency. So many IoT, because we are talking about IoT devices, so many IoT and edge devices operate under strict power constraints. So intelligent scheduling mechanisms, context-aware mechanisms, when to switch on, when to switch off, when to listen, when to forward kind of techniques has to be there. So such kind of intelligent scheduling and energy-aware computing mechanisms are needed for such kind of critical applications, and or if you are going for some long-term sustainable kind of applications. Likewise, as the project, actually I'm mentioning about the Periyar Basin project also, whenever we are putting some floating sensors on the Periyar Basin river, it also has to do such kind of monitoring for a longer period. We cannot often go there and recharge the batteries. It has to monitor the real-time parameters on a real-time basis, 365 days, 24/7. So we need to go for some kind of energy-aware scheduling kind of mechanisms for long-term sustainability. Most importantly, all these limitations, all these dimensions cannot be optimized independently, right? We cannot work on these dimensions. We cannot work on energy dimension alone. So that's why these dimensions are not independent. They are connected, they are dependent to each other, so they cannot be optimized independently. So decisions, why? Because decisions in one layer directly affect the others. So effective edge intelligence therefore relies on different joint optimization across different devices, edge nodes, the cloud, running a tightly coupled, tightly integrated intelligence system rather than a collection of different isolated compartments. So that's why nothing like, even though it is not about AI or different dimensions, AI, IoT, or any other kind of cloud computing systems cannot work on independent fashion. They are not isolated compartments. They are widely connected in order to have a sustainable kind of if we are going for building a sustainable kind of ecosystem. Okay, so these dimensions cannot be optimized independently. We need to go for a joint optimization, right? Can I take 10 more minutes, ma'am?
Sure, sir, sure.
Sure, okay. It's 8:53, that's fine. Okay, so so these are the main architectures for edge intelligence. So we have with the as I told you, there is a rapid growth happening this IoT and through different 6G frameworks, network, etc. So centralized cloud processing is, we understood now that this processing is no longer sufficient. So edge intelligence addresses this by shifting all those computation, etc. So here you can see some examples of that. So these include, as I told, like AWS, but these are different frameworks. These are not just the company AWS, the generic AWS cloud platforms. There are, well-acclaimed, user-based, user-specific, or use case specific kind of frameworks, which is all, we can say that these are the mainstream AI frameworks, like include AWS IoT Greengrass, Microsoft Azure IoT Edge, Google Cloud IoT Edge, Open Horizon. So you can see, like, there is uh, one interesting project of Microsoft, which is again edge centric. You can Google it and find out what is known as Farm Beats, FARM, Farm Beats. Farm Beats is an intelligent AI-based, edge-centric, edge intelligence-based IoT solution for precision farming. And this is actually a combined effect of Microsoft along with University of Utah in USA, along with University of Illinois. They are actually working on this kind of precision farming along with the UAVs and smart tractors, different kinds of machines and all, intelligent farming machines. They could have a predictive farming and all those kind of stuff. And they named that project known as a Farm Beats. And this Farm Beats actually connected, it is now available in 50, almost 40 or 50, like 40 states, I think, in America. And the majority of the farmers now, they are leveraging this kind of Farm Beats kind of intelligent platform. So similarly, AWS, Amazon Web Service also, they're having something called as AWS IoT Grass, Azure IoT Edge, Google Cloud IoT, then Intel Open Vino, etc. So each of those frameworks adopts a different, they are having a different design philosophy, varying in the reliance on the cloud services, deployment complexity, so suitability, sustainability, suitability for different application scope or scenarios. So among these, I can say that AWS, that IoT Greengrass, which is a representative and widely adopted solution, because it actually, as I said about the Microsoft Farm Beats, it extends the cloud capabilities to edge devices through a kind of a modular architecture that is being showcased over here in this diagram. So it extends the cloud capabilities to the different edge devices through this kind of architecture that could manage different runtime executions. They could go, and almost all the communications are secure communications and state synchronizations, and there are different isolated execution environments as well. So Greengrass, kind of a framework from AWS, offers or operates through different phases. Like there is an initialization phase, you can see there is an invocation phase, there is a computational shutdown phases, etc. All actually enables different manage messaging. They enables different device computations, on-device computations, efficient messagings, data caching, and machine learning kind of inferences. So performance evaluations nowadays, from that paper, I understood that performance evaluation shows that extremely low operational latency or in the order of microseconds are getting through this kind of AWS IoT Greengrass. Okay, so this is all about these mainstream architectures. Then moving on. So when we compare different computing, edge computing frameworks, this provide a comprehensive, a comparative overview of widely used edge computing frameworks that support edge intelligence across different dimensions, like whether it's a cloud dependent or not. How about the operational complexity? How about the deployment, that difficulty? What are the security capabilities and what are different application scenarios? So AWS IoT Grass, as we discussed in the previous slide, it shows a high dependency on the AWS cloud itself, but in return, it offers a lot of strong security capabilities and broad applicability across different heterogeneous industries. So this operational, these kind of frameworks is highly operational, and the deployment complexity sometimes will be high because it is depending on different varieties of industries. So deployment complexity will be quite high. That reflects its functionality to be more cloud centric rather than edge centric. Then we have the Microsoft Azure IoT Edge following a similar philosophy and similar other kind of computing frameworks are available here, right? Then okay, different architectures. I'm just moving on. It's already 8:59, so I'm just skipping some of these kind of architectures, and so that I can give you some insights about the. You can just these are all generally available. Like what are the edge-centric architectures or frameworks? One from Intel, one from Google, one from Microsoft, and one from Amazon. I'm just moving on, and so here you can see like a different computational offloading and resource management in 6G. So so here you can see that we are moving into the first optimization domain of the EI framework, like how we can do the computational task offloading and resource management. So here also you can see that the features of 6G technology here, like there are working on terabits per second. So with terabits per second level, the bandwidth and the end-to-end latency is expected to be 0.1 millisecond. 0.1 milliseconds. So 6G enables a much more refined and flexible kind of execution model. So instead of moving towards building some static decision kind of communication frameworks, edge intelligence adopts a kind of dynamic, dynamic and hybrid kind of offloading approach. So each task here, or even each part of the task, is evaluated in real time based on the computational complexity, current networking conditions, and the capabilities of the device and edge servers. Okay. Then I'm just moving to the yes. So some of the challenges here are the technical challenges that which is again copied from the same paper, which arise mainly due to the mismatch between the advanced AI requirements and the limited capabilities of edge devices. So there are limited edge computing capacity of edge devices. So that is one of the important challenge. Limited computing capacity of edge devices. So we know that edge devices can be think of like a small sensor to some embedded system. Sensors could be a part of edge devices. Gateways are a part of edge devices, and embedded systems are also a part of edge devices. We know that all these categories of devices or systems have strict constraints in forms of memory, processing power, energy, etc. So running complex AI models directly on devices is often infeasible. That is one challenge. Then in order to address that, I told you like we need to go for some model compression, pruning and quantization, etc. to reduce the model size. And you need to work on the computational overhead while accepting there could be a trade-off. There could be a trade-off between accuracy and computational overhead. But if you want to run such kind of models at the edge side, you need to severely work on the model compression side, pruning and quantization side. And that are the methods to reduce the model size and computational overhead. So there should be a balance between a trade-off between the accuracy and computational overhead. Then there is a resource mismatch between different 6G networks and IoT devices. I told you that 6G networks is highly, it is extremely high. It offers extreme high bandwidth and ultra low latency. So many IoT devices cannot fully exploit these capabilities due to these hardware limitations. So that's why we talk about task offloading, distributed computing, and cloud edge collaborations. Then the third important limitation is difficulties in deploying complex AI models. I told you about you need to work on computationally incentive models. State-of-the-art models are majoritarily, they are all into computational incentive models. So you need to work on the lightweight models and federated learning, etc., to allow intelligence to be deployed, intelligence to be extended efficiently without requiring any kind of centralized data collection. Okay, and also the one of the other thing, we cannot avoid security and privacy, right? Security and privacy constraints cannot be avoided at any cost. So that becomes, so this is a major next challenge category concerning security and privacy, which becomes even more critical in large scale distributed EI systems. So data distribution security risks are there, right? Between data exchange between devices to devices. I told you about the UAV to UAV communication or UAV to the ground communication, etc. Edge nodes, networks. So making all of them vulnerable to such kind of different kinds of inside and external side attacks, intrude or extrude attacks. So end-to-end encryption and secure communication protocols are essential to ensure such kind of data integrity and confidentiality. Okay. So these are some of the challenges that as a researcher you need to look at. And when you look into the development trend of edge intelligence, now people are working on the multi-domain collaboration side. People are working on communication with AI, communication with different computing paradigms, applications, etc. Because I told you in the previous slide that without coordination across these domains, systems becomes standalone. They become fragmented. They are working in independent compartments, etc., and that makes the entire system inefficient. So we need to look forward to have related technologies, some interoperability and compatibility should be there. So for all practical applications, sustainable development initiatives, etc., we need to look forward to have the collaboration platforms. That's why FL has a huge role to play here. So these are some of the, and also now people like me, since I am into cybersecurity department of IIIT, we are working on different kinds of access control models as well, like role-based access control models and attribute-based access control models and all. So these are all related technologies where people are working on different blockchain assisted access control models. People like me, they are working on cloud-centric, edge-centric, attribute-based access controls and role-based access control models, where we can provide a level of security, because all the times when we are putting all these kind of security mechanisms, etc., in the edge side, we need to have a strong, balanced approach between security, safety, and practicality. So strong cryptographic mechanisms will always give you security, but at the same time, it reduces practicality. So whenever we go for some practical, flexible kind of environments, we need to look forward to have a blockchain assisted. Blockchain-based systems are nowadays, that many practical applications, you can see blockchain-based systems are there. Therefore, secure and private, even for private, financial transaction, etc. For example, they're all blockchain assisted. So these are all some of the development trends happening at the edge side as well. People, if you're interested, you can work on secure access control models. One of the models is the attribute-based access control models or role-based access control models or blockchain-based trust mechanisms, the blockchain log mechanisms, etc. We are actually working on blockchain-assisted federated learning at the application layer of this, a multi-layer UAV security project. Okay. Then, okay, I think almost I have covered a majority of the things. So here you can see that these are the open research directions. You have to work on this cross-layer co-design of, because people are now, that's why in my project also, I'm not concentrating only on a single layer. So it's a multi-layer approach, a physical layer with data link and especially with application layer as well. So cross-layer co-design of AI, because it is not a single standalone system. We need to get, it is a foolproof kind of secure, multi-UV security we have to develop. So we cannot work on a single layer. We have to go for a cross-layer approach. So majority of the times, if for data link layer, we are working on CHA-20, Poly 150 kind of algorithms. The same capability can be extended towards the physical layer. Physical layer, like, we have the physical median dependent and the other layers, right? Physical layer as well, where these kind of, we could extend the capabilities of this CHA-20 150 polymer 150 algorithms for applications like edge based UAV to ground applications. So ground, we know that it's a physical air approach. So we are actually, there is a SWAM kind of a communication. We have a Qn drone that is a prime drone, and this drone will be forwarding the collective data from all the drones to the ground station. There we are using Chacha 20, 150, Polymer 1, Poly 150 kind of algorithms for end-to-end encryptions. So these are some of the open research directions that you can look into. So always go for some papers, especially my humble suggestion for all of you, if you are new to this area, you can read papers on IEEE communication surveys and tutorials, or you can go and read IEEE communication magazines to have good understanding about the UAV assisted communications, UAV edge assisted communications, AI assisted edge, AI assisted. Then majority of the people, if you're looking for some funding from external funding and all, you need to have a very good use case. So nowadays, Government of India through this ANRF or any other kind of, Anusandhan Research Foundation or MIT, they are not actually funding the conventional theoretical based projects. Those days are past. We need to have a minimum TRL level 3 or 4 at our end. So we have to convert all our theoretical ideas into product, and we do have the practical evidence with us. We should provide them a practical, a prototype kind of evidence. Okay, we have completed to this, and in order to move forward.
Participants, please mute your mic. Dear participants, sir, I accidentally muted you. Could you please unmute yourself and you can continue, please. Dr. Ragesh, am I audible? Hello? Hello? Dr. Ragesh?
Okay, so that's all about this presentation. So I have given, because with this 1.5 hours, I have given most of the kind of my ideas, my personal experiences related to edge computing and intelligence. So if you have any questions, you can ask me. You can go through my profile and reply to you also. If you want to collaborate with any kind of projects related to drones or IoT or similar kind of AI-based IoT projects and all, I'm happy to be associated with any one of you. So we aggressively work on different kinds of projects nowadays, especially on ANRF and many things. And like recently, we got many projects through ANRF and this ACN grant and through these kind of iHubs and all. So if you people are interested in some of these things and all, I'm happy to associate with you. So because there should be some kind of takeaway, there should be some kind of outcome through these kind of discussions. Otherwise, it becomes generally a monologue kind of. It has to engage in a dialogue, and only such kind of FDPs will become more more effective. Otherwise, it will be just another kind of a talk. So that's why I just mentioned about the different avenues where you can submit proposals based on such kind of edge intelligence, but always look for some kind of use cases. So with that, I'm concluding my talk for the time being. And if you have any questions, I'm happy to answer. Thank you.
So I'm really happy that we are able to keep up our association starting from Sengis to till today.
Yes,
now, but we'll take we'll continue our discussion offline, sir.
Okay, sure. I know that it's only 9:15
from your work, and I do not want to trouble you. I'm sorry. I know.
No. Since see that I'm still in my office now, I want to travel to Kaladi in my bike. actually.
I'm sorry, and thank you. Thank you so
Okay,
much.
okay then. Thank you so much. Yeah. Okay.
Thank you very much, sir, for the insightful session.
Thank you. Yeah. I think I'm trying to unmute myself, but some okay. Thank you very much. So no more questions, I think, from the audience side. Okay, thank you then. Shall I leave?
Yes, yes.
Okay, thank you.
Please take rest. Yes, thank you.
Dear participants, please note that the feedback link for today's sessions, both first and second sessions, have been shared in the WhatsApp group. Kindly fill it and kindly fill it before 10 o'clock. Also, the FDP feedback, a document has been shared on the WhatsApp group. So you are requested to kindly download it and update the details for all the update the feedback and other details regarding all the sessions, all the 6 sessions for the 6 days. We will be sharing a Google form tomorrow, and you can upload your document in PDF format in that Google form. So kindly make sure by tomorrow evening you have completed the document. So thank you very much. Have a good night. We'll meet tomorrow, which will be the last day of the FDP. Thank you very much.
So just a gentle reminder, tomorrow the session starts at 2 p.m.
Yes, participants, kindly note that this first session tomorrow will be from 2 p.m. to 3:30 p.m. And the second session will be from 3:30 to 5. Thank you very much. Good night.